There's something about the moment just before sleep, not sleep itself, but that specific few seconds when your body decides it's done holding itself up. You feel it in your shoulders first, probably. A slow permission, weight you forgot you were carrying, just releasing. And somewhere in that descent, you're not quite anywhere. Not awake, not asleep, just crossing. I want to start there. Not because it's poetic, well, maybe a little. But because what I want to talk about tonight begins with a crossing that doesn't feel like anything either. Most of us carry a fairly stubborn idea about where things end. Surfaces, edges, the place where one thing stops being itself and becomes something else. A wall when your knuckles meet it. The cold of a window pane in winter. Even water has that. The moment your hand breaks through, there's a boundary, a sensor and a signal that says, you are now somewhere different. Black holes don't offer that. And that's the thing I keep coming back to, the thing I've been circling around for a while now on this channel, on The Sleepy Physicist, where we come to let big, strange ideas settle rather than fight them. The thing that I find quietly unsettling about black holes isn't the darkness or the gravity or even the fact that nothing returns. It's that the entry is invisible, not invisible like hidden, invisible like there is genuinely nothing to see. This channel runs without ads, without institutional funding, without a studio. It's just me, research, and the patience of people who've decided this kind of late-night science is worth something. If you want to help keep it going, there's a Patreon linked in the description. Even a small contribution makes a real difference to whether this work continues. The people who found their way here and decided to stay, you're the reason this exists. That's not something I take lightly. Sitting with you in the quiet week after week, that steadiness means more than I usually say. Now, the floor. Let me try to describe what a black hole's edge actually is, and I want to do it without the vocabulary that usually makes it feel like theatre. The event horizon is a surface in space, not a solid surface, no material, no membrane, nothing you'd push against. It's a geometric location, a line in the structure of spacetime that marks the point past which outward motion becomes mathematically impossible. You could pass through it right now, theoretically, and feel nothing. No change in the temperature, no sound, no pressure shift. The air in front of you, or the space or whatever surrounds you, it would just continue. And behind you, quietly, the universe would have sealed. That's the part I think we skim over too quickly. The entry is a non-event. Actually, let me correct that slightly. It's not quite that nothing happens. Something does happen, but only in the math, and only in relation to an observer far away. From their perspective, watching you fall, you'd appear to slow. Light from your body would lose energy climbing out of the gravity well, shifting toward red, dimming. To them, you would seem to freeze at the edge, darkening over what would look like infinite time, never quite arriving. An image that just gets fainter. But from inside the fall, nothing signals the crossing. Your watch keeps time, your thoughts keep moving. You pass through the most consequential threshold in the known universe, and the universe declines to announce it. There's a physics term for this, freely falling frames. And what it means, stripped of jargon, is that gravity doesn't feel like a force to the thing it's pulling. You felt this in an elevator when it drops. For a fraction of a second, you're weightless. Not because gravity stopped, because you're falling with it. The sensation of gravity requires resistance, something pushing back. Inside the event horizon on the way in, nothing is pushing back. There is only the fall, and the fall is frictionless and silent and completely ordinary right up until it isn't. I'm going to be honest about something. I used to picture the horizon like a surface of black glass. That persistent image, the sphere of absolute dark, the edge you could see if you were far enough away. And it's not wrong exactly, but it's wrong in the way that a map of a country is wrong. The detail you need isn't on there. The event horizon has no local physical reality. Stand next to it, if you could, and you would have no idea. It is defined entirely by its consequences, by what it means for everything that comes after, not by what it is, but by what it does. That's a strange kind of existence for a place that contains so much of what we find important. And the location of the horizon isn't even fixed in a deeper sense. It depends on the history of the space-time around it, on what's falling in, on what's more near. For a black hole that's actively swallowing matter, the horizon shifts, breathes almost. In principle, the event horizon today is partly determined by what will fall into the black hole in the future. That sounds like I got that backwards. I didn't. The mathematics of general relativity allows the global structure of space-time, including the location of horizons, to be sensitive to what hasn't happened yet. The horizon knows what's coming. I want to be careful here because this is one of those places in physics where accurate description sounds like mysticism, and it genuinely isn't. The mathematics is precise. The horizon's location is real and calculable. It's just that the calculation requires knowing the entire future history of the space-time, which, no, we can't do that. But the point is that the horizon isn't a thing sitting there in space like a fence. It's a feature of the geometry that includes time. Outside my window right now there's a streetlight that flickers, has been for months. It has nothing to do with any of this, but I notice it every time I sit down to write something about light, which happens more than you think. It flickers and my eye catches it and I lose a sentence. This chapter has lost probably 4 sentences to that light. Let me get back to falling. When physicists talk about what it would be like inside a black hole, they're making claims that can never be verified by an outside observer. Everything that crosses the horizon is, in a very clean and literal sense, cut off from the rest of space-time. Not hidden, cut off. There's no in-principle method of communication, no current technology, and no physics. The causal structure of space-time past the event horizon simply doesn't connect to ours. This is different from distance. Something 1 trillion light years away is still in the same space-time. Its light could still reach us, given enough time. The region inside a black hole is not in our space-time, not in the sense of being accessible. It is, and here I'm aware this word is doing a lot of work, elsewhere. Elsewhere in a way that has no map. The thing is, this should be terrifying, and mostly it isn't. When you sit with it at the right hour, at the right angle of tiredness, it becomes something else. It becomes a kind of information about what space-time actually is. Not a fixed backdrop, not an empty stage. Something with structure. Something that can be shaped into a region with no exit. A place that exists within the universe and is simultaneously unreachable from within it. There are places you can go that the universe cannot follow. Not many, but they exist. I keep using the word surface and then undoing it, because the horizon resists the word and I keep reaching for it anyway. Habit, maybe. We are tactile things, all of us. We understand reality in terms of surfaces, pressures, thresholds you can feel, and here is a threshold that you feel nothing at. You pass through the most one-way door in physics and the door doesn't push back, doesn't even make a sound. The physics only asks one thing for you, that you be falling, freely, without thrust, without resistance. If you are, if you just let the gravity have you, the crossing is seamless. Embarrassingly so, like the universe put the most consequential line it knows how to draw and then forgot to mark it. Direction changes past that line. One of your 4 dimensions of freedom, the one that used to point away from the center, begins pointing the same direction as time. Forward only. No return, not because of force, because of geometry. The shape of space-time past the horizon is such that all futures lead inward. You aren't pushed, you just run out of direction, and I'm not sure I have a cleaner way to say it than that. You run out of one of the directions, the one that used to lead out. It folds into time, and time only moves one way, and so you do too. What comes after this, what waits further in, what the mathematics says about the deep interior, what happens to the geometry past a certain point, that's for the next few hours. Tonight, I wanted to start here, at the edge that isn't an edge, at the crossing that doesn't announce itself, at the place where the floor disappears so gently you don't notice it's gone. Gravity is patient. That's the thing about it that took me the longest to absorb, not its strength, not its reach, just how patient it is, how it sits there, how it doesn't announce its intentions or shift in mood or occasionally take a day off. You wake up and it has been waiting the whole night, not leaning, not pulling with any particular urgency, just maintaining the same steady claim on every atom you contain, patient in the way that a debt is patient, not threatening, just there. Most forces, if you think about them as forces, have a physical story. Something pushes, something pulls, there's a medium, there's a carrier particle doing the work. Electromagnetism has photons shuttling between charges. The strong nuclear force has gluons binding quarks in a kind of frantic, ongoing negotiation. But gravity, general relativity's version of gravity, the one that becomes important near black holes, doesn't have a push or a pull at its center. What it has is a shape. The shape is of time. I want to try and explain this without turning it into a lecture, because it isn't a lecture kind of thing. It's more like you already know it, in your body, and the physics just gives you language for something you've been experiencing without the vocabulary. Stand still for a second. You're not falling. The floor is pushing up against your feet, and that push is what you register as weight. But take away the floor, step off a ledge, enter a free fall, find yourself suspended in deep space away from everything, and weight disappears. The gravity doesn't disappear, the Earth is still pulling, but with nothing resisting it, nothing pushing back, you don't feel it anymore. Gravity to a freely falling body is imperceptible, completely. This isn't an approximation or a simplification. It is precisely what Einstein noticed, and he called it, straightforwardly for him, the happiest thought of his life. What you feel when you feel gravity is resistance, not gravity itself, the floor refusing to let you go where gravity wants to take you. Here is the actual machinery, though I'm going to say machinery, and immediately wish I'd used a different word. Let me try again. Here is the actual situation. Mass. Any mass. A planet, a person, a grain of dust. Changes the geometry of space-time around it. Not symbolically, physically. The 4-dimensional fabric that contains all events, all trajectories, all possible paths through space and time, it curves in the presence of mass. And when it curves, the straightest possible paths through it, the paths that require no thrust, no acceleration, no applied force, are no longer what we'd call straight in ordinary space. They bend, they arc, they fall toward mass, not because mass reaches out and grabs them, but because toward mass is, in curved space-time, simply the most natural direction to go. A ball thrown into the air traces a parabola. That parabola is, in 4 dimensions, the straightest possible line available to the ball. Straighter in the geometry of space-time than the path you'd take standing still. This is not a metaphor. This is geometry. Gravity is not a force doing something to objects, gravity as objects doing what geometry tells them, which happens to look like a force. The part that makes my brain do something uncomfortable, not confusion exactly, more like a low-level protest, is the time component. When mass curves space-time, it curves time as well as space, not just space. Time clocks near a massive object run slower than clocks far from it. This has been measured. GPS satellites run fast compared to clocks on the ground by about 45 microseconds per day, and that drift has to be corrected for continuously, or the positioning system fails. The correction is for the curvature of space-time near Earth's surface. We use general relativity every time we navigate somewhere. The time dilation isn't a side effect, it's structural. Time runs at different rates depending on how deep you are in a gravitational well. Deeper means slower, and this variation in the rate of time is precisely what curves the paths of objects, because everything moves through space-time, including things we think of as sitting still, and when time runs differently in different places, the paths those objects take through the combined four-dimensional structure get bent toward the region where time runs slowest, toward mass, toward depth, toward the bottom of the well. The tea on my desk has gone cold. I notice this the way you notice things you've been ignoring all at once after the fact. There's a concept called a geodesic. It sounds technical, and in practice it's just the path through space-time that requires no force to follow, no engine, no thrust, no muscle. The path pure inertia takes when there's nothing interfering. In flat space-time, and far from all mass where gravity is negligible, geodesics are straight lines, constant velocity the way you'd expect. In curved space-time, geodesics curve, and every freely falling object in the universe is, at every moment, following a geodesic. The planet orbiting its star isn't being pulled into a loop, it's following the straightest available path through a geometry that happens to curve around the star's mass. The orbit is straight, locally. From inside the path, with no awareness of the surrounding curvature, it is simply inertia continued. This is the thing I keep coming back to, the thing that seems like it should feel stranger than it does. The geometry does everything. There's no invisible hand, no thread, nothing running between the sun and the earth doing the work of attraction. Just shape. The shape of the stuff that space and time are made of, deformed by mass, and every object in the universe following that shape as faithfully as water following a slope. Now, take this and push it harder, near a very massive object, a neutron star, and more so a black hole. The curvature isn't gentle. It isn't the shallow curve of Earth's gravity, which is strong enough to keep you grounded, but weak enough that you can stand up, walk across a room, lift a glass. Near a black hole, the curvature of space-time steepens dramatically, and the consequences of that steepening become strange in ways that flat space-time intuition doesn't prepare you for. Light, which follows geodesics because it has no choice, it has no mass, no engine, it simply travels the geometry, begins to curve noticeably. Paths that point away from the black hole start bending back. Far enough in, paths that look like they're pointing away actually trace arcs that return. Closer still, the only outward-pointing geodesics that don't curve back are the ones that started out pointing exactly, precisely away, and even those take infinitely long to reach any finite distance from the perspective of an observer far removed. And at the horizon, which we visited last night, the geodesics have been curved so thoroughly that every future-directed path leads inward, not because something blocks the outward ones, because there are no outward ones left. The geometry used them up. I want to be honest about what this is and isn't telling us. General relativity describes how Math shapes space-time with extraordinary precision. It predicted gravitational waves, which were detected a century after prediction. It predicted the bending of starlight around the Sun, confirmed in 1919. It describes the expansion of the universe, black holes, the slow drift of orbits due to space-time geometry. It is one of the most tested theories in the history of physics, and it keeps passing. But it doesn't tell us what space-time is made of. That question, the substrate question, whether space-time has a fundamental granularity, whether it emerges from something more elementary, and that's open. The theory treats space-time as a smooth, continuous field and works with that assumption brilliantly until it doesn't. The places where it doesn't are the places we're headed. For now, the geometry is real, the curvature is real. Time running slower near mass is real, measured, corrected for in machines you carry in your pocket. That's the foundation we're standing on. It curves. That's the whole sentence. Space-time curves in the presence of mass. And that curvature is what gravity is. And every consequence we'll talk about in the coming hours, the light that can't escape, the geometry that closes in, the singularity that waits at the centre, all of it flows from this. From the simple, stubborn, patient fact that mass tells space-time how to bend, and bent space-time tells everything else where to go. The mathematics that describes this is beautiful. I say that knowing it's a cliché, but also knowing it's true in a specific way. Not beautiful like a painting, but beautiful like a proof, where you start somewhere ordinary and the logic moves and moves, and at the end you arrive somewhere that couldn't have been predicted, and yet was always there, waiting in the structure. And somewhere in this curvature, if you follow it far enough, if you let the mathematics run without stopping it when it gets uncomfortable, you arrive at places where the curvature stops behaving and the geometry does something that the theory itself cannot describe. That's what the centre of a black hole is, not a place. A problem with the description. A place where the map, this beautiful, precise, tested map, simply ends. Nothing about a star looks like it's waiting to become something else. That's worth sitting with for a second. You look at a star, really look, on a clear night when the atmosphere is cooperating and the light isn't competing. And what you see is completeness. A thing that has fully arrived at what it is. Burning, present, its own argument for existing. There's no visible tension in it, no sign of the negotiation happening at its centre. No indication at all that what you're seeing is a temporary settlement between forces that will, eventually, lose patience with each other. Stars are very good at looking permanent. What's actually happening inside one is a deal. A massive star, and when I say massive I mean something 8, 10, 20 or more times the mass of our Sun, which is already a thing so large that 1,000,000 Earths would fit inside it and there'd still be room, is in constant negotiation between two tendencies that want opposite things. Gravity wants to compress, everything inward, always the patient insistence we talked about last night, the steady claim that mass makes on the space around it. And pushing back against that compression is pressure, the outward force generated by nuclear fusion happening in the core. The core is eating itself in a very specific and methodical way. Hydrogen fuses into helium. The energy released pushes outward. Gravity pushes inward. They meet in the middle, and the star holds its shape, not frozen, not static, but balanced in a dynamic that can last millions of years for the most massive stars, billions for smaller ones. The Sun has been running this process for about 4.5 billion years, and has roughly that long again before things start to change. We are, as far as stellar timescales are concerned, at half-time, but the fusion can't continue indefinitely on the same fuel. Hydrogen runs low in the core. The star adjusts. It's surprisingly adaptable, actually, and begins burning helium. fusing it into carbon and oxygen. The physics shifts slightly, the energy output changes, the outer layers respond. More adjustments. Carbon begins to burn, then neon, then oxygen. Each successive fuel releases less energy per reaction, burns faster, lasts a shorter time. What took millions of years at the hydrogen stage takes thousands at the carbon stage, hundreds at later ones. By the time the core is burning silicon into iron, the process has accelerated so dramatically that the final stage lasts approximately 1 week. 1 week. Out of a stellar lifetime of millions of years, the last fuel burns in a week. Iron is where the deal breaks. Every element up to iron releases energy when its nuclei are fused together. That's the physics of nuclear binding energy. Lighter elements, fused, produce heavier ones, and the mass difference becomes energy, the energy that holds the star up. But iron is different. Fusing iron nuclei doesn't release energy, it absorbs it. Iron is, and I don't know a more precise way to say this, iron is the dead end of stellar nucleosynthesis. It's what you get when fusion has extracted everything it can from a chain that started with hydrogen. The core fills with iron, and iron just sits there, inert, not burning, doing nothing useful. Stubborn element, genuinely useless to a dying star. The iron core grows. As it grows, gravity's claim on it intensifies. There is no fusion energy pushing back anymore, nothing generating the outward pressure that kept the geometry honest. The core is just mass, accumulating with nothing to say for itself. Outside my window the rain started about 20 minutes ago. Fine rain, the kind that sounds like static. I've been listening to it without noticing the way you listen to a lot of things. At a certain point, when the iron core reaches roughly 1.4 times the mass of the Sun, a threshold with a name, the Chandrasekhar limit, the pressure from electrons, which have been doing some of the work of holding the core up, can no longer resist the gravity. This isn't a gradual thing. It isn't the slow dimming of something running low. The core collapses. The entire iron core, a mass greater than the Sun compressed into a sphere roughly the size of Earth, collapses to a sphere roughly 20 kilometers across in somewhere between 1/10 of a second and half a second, depending on conditions. That's the conversion. Sun mass to city size in less than a second. I've written that sentence before and it still does something weird to my sense of scale every time. Not awe exactly, more like the feeling of reading a number that clearly means something and being unable to make your brain receive it at full volume. What stops the collapse, in most cases, for most massive stars, is neutron degeneracy pressure. As the core compresses beyond the point where electrons can provide resistance, the protons and electrons in the core are forced together, combining into neutrons. The core becomes, essentially, a single enormous atomic nucleus. Pure neutrons packed to nuclear density, and neutrons at that density resist compression with a stubbornness that rivals anything in physics, a quantum mechanical prohibition on packing fermions into the same state, the Pauli exclusion principle operating at macroscopic scale. The collapse hits this resistance and bounces. The outer layers of the star, which have been falling inward at a significant fraction of the speed of light, slam into the suddenly rigid neutron core and rebound outward in a shockwave of energy, the explosion we call a core collapse supernova, one of the most energetic events the universe produces, releasing in a few seconds more energy than the Sun will emit across its entire 10 billion year lifetime. Most of that energy incidentally comes out as neutrinos, not light. Neutrinos, particles so weakly interacting that they pass through the entire Earth with negligible resistance, pouring out of the collapsed core in a burst that briefly outshines, in neutrino luminosity, all the stars in the observable universe combined. the light is almost an afterthought. But this doesn't always happen cleanly. For the most massive stars, those significantly above a certain mass threshold, somewhere above 20 or 25 solar masses, though the exact number argues with itself in the literature, the neutron core may not be able to hold. The mass falling inward is too great. The bounce may stall. The shockwave may fail to propagate. The outer layers, instead of being blasted outward, continue inward. Everything falls in. No spectacular light show, no shockwave. In some cases, possibly theoretically, there are arguments. The star simply winks out, disappears from the observable universe mid-burn. People have looked for this. There are a handful of candidate stars that vanished from catalogues without producing a detected supernova. One called N6946-BH1, a massive red supergiant that was being monitored in a galaxy about 22 million light-years away, brightened briefly in 2009 and then was gone. Not exploded. Just gone. We don't know for certain what happened. We think we know. What remains in the collapse scenario that produces a black hole is not a neutron star but something past one. The matter continues compressing past nuclear density, past any density at which known physics provides resistance. Inward, always inward, until... And this is where the sentence runs into territory we'll spend entire chapters on. Until the mathematics stops giving clean answers, a new geometry begins, not an explosion, not even a death quite. That word implies an ending that happens at a location you could visit, something with the decency to leave a mark. What forms instead is a region of spacetime with different rules. The geometry seals. What was a star becomes first a surface nothing can return from, and then an interior where the curvature does things that the outside the universe cannot track and cannot follow and will not ultimately be able to describe. The star spent millions of years becoming a specific kind of object, a burning, balanced, patient thing, and then, in the time it takes to draw a breath, it became something else entirely. The patience ran out. The deal collapsed. The geometry sealed itself shut. What's left isn't the star anymore. What's left is the question of what happened to the space it used to occupy, and what that space is now doing, in the dark, alone, unreachable, with all that mass and all that history, and nowhere left to go but in. What does it mean for a theory to break? Not for a theory to be wrong. That happens all the time and is mostly fine. That's the process. That is how the whole thing's supposed to work. But to break. To arrive at a situation it was designed to describe and produce, instead of a description, a number that has lost all connection to physical meaning. An infinity where a quantity should be. A division by zero, hiding inside the most precise mathematical framework we have for understanding space and time. That's what happens at the centre of a black hole. General relativity, which has been right about almost everything we've asked it, the bending of light, the existence of gravitational waves, the behaviour of Mercury's orbit, the way GPS satellites need corrections for time dilation, produces, at the centre of a black hole, a prediction of infinite density and infinite curvature. Infinite, not very large, infinite. And physics, as a discipline, treats infinite answers the way a good mechanic treats a smoke smell from an engine. Not as a result, as a symptom. The word we use is singularity. It has a formal definition. A point where the mathematical description of a spacetime breaks down, where curvature scalars, the quantities that measure how curved the geometry is, diverge without bound. The geodesics, the paths we talked about last chapter, the straightest available lines through the spacetime, they terminate. They reach the singularity and simply stop in finite proper time with nowhere to go, not because something blocks them, because the space-time ends there. No more positions, no more moments, no more geometry to exist inside. This is different from a coordinate singularity, which is a more polite kind of problem, an artifact of the coordinate system you're using, like how longitude lines seem to converge at the poles of Earth in a way that panics the math but doesn't panic the physics. The event horizon, actually, is a coordinate singularity in some reference frames. It looks like a problem, but it isn't one. You can change your coordinates and it smooths out. The singularity at the center is different. Change your coordinates all you like. It's still there. It's a real feature of the geometry. Or rather, and this is where I always have to slow down, it's a real failure of the geometry, a place where the geometry stops being geometry. Here's the thing that took me an embarrassingly long time to really sit with. The singularity isn't a place inside the black hole the way the kitchen is a place inside a house. It doesn't sit at a specific spatial location that you could, in principle, point toward. Once you're inside the event horizon, as we established, the direction pointing toward the singularity is not a spatial direction, it's a temporal one. The singularity is in your future, not in front of you. You aren't travelling toward it the way you travel toward a wall. You're travelling toward it the way you travel toward next Tuesday. You cannot avoid next Tuesday. This is what people mean when they say the singularity has no address. Not that it's hard to locate. That location in the spatial sense isn't a category that applies to it. It exists in the future of every world line inside the horizon. It is when, not where. And it arrives, the phrasing is unavoidably strange, it arrives for you rather than you arriving for it. I've been trying to think of a comparison for this, and everyone I reach for is wrong in some important way. A deadline feels too manageable. A wall feels too spatial. The end of a film reel is close but too mechanical, too cheerful somehow. The closest I can get, and I'm not fully happy with this, I want to say that up front, is that it's like trying to move in a direction that exists only in one map and not in the territory. You've been navigating by a map that has always matched the ground reliably for your entire journey. And now you've arrived at an edge of the map, and past the edge is not more territory that the map hasn't drawn yet. Past the edge is a region where the concept of territory stops applying. The map ends, not at the shore. At the shore there'd still be ocean. The map ends at a place where extension itself, spatial extension, temporal extension, the basic furniture of having somewhere to be, gives out. The singularity is where the map ends. There's a version of this that physics handles with relative composure, which is to say, most physicists think the singularity is not real. Or rather, they think it's real in the sense that it's a genuine prediction of general relativity, but they don't think it's real in the sense of being a feature of actual physical space-time. The singularity in this view is what you get when you push general relativity past the domain in which it's valid. A symptom of incompleteness, a signal that a better theory is needed. The better theory is quantum gravity, which does not yet exist in complete tested form. That's the situation. We have a theory that works everywhere we've tested it and produces, in one location, a result that is physically absurd, and we have a placeholder, quantum gravity, that we believe will smooth the absurdity out, based on how similar situations have gone in the history of physics, but which we cannot yet write down in a form that makes testable predictions about black hole interiors. So we are, on the question of what actually happens at the centre of a black hole, operating on informed expectation, educated confidence, a belief shared by most of the relevant physicists that the singularity is not the last word. But it might be. Someone is playing music in a nearby apartment low enough that I can't identify it. just a recurring bass note, patient and indifferent, going about its business while I try to write about the end of space-time. The singularity is where the map ends. I keep coming back to that phrasing not because it's the best one, but because it resists being replaced. Every substitution I try is either too dramatic, implies cataclysm, fire, some decisive event, or too gentle, implies a quiet stopping that doesn't capture the mathematical violence of curvature diverging toward infinity. The map ending gets at something true. The tools for description, which have worked everywhere else, simply cease to function. Not the world ending, the description ending. Whether those are the same thing is not a question physics can currently answer. Some theories try. Loop quantum gravity, which treats the geometry of spacetime as fundamentally discrete, granular, made of finite minimum units rather than infinitely divisible smooth fabric, predicts that the curvature at a black hole's center is large but not infinite, very large, incomprehensibly large by any ordinary measure, but bounded, finite, and in some versions of the theory, the collapsing matter doesn't terminate at the singularity but bounces, compresses to a maximum density, and then expands outward again, possibly into a different region of spacetime, possibly into what some models describe as a white hole. The bounce is speculative. String theory has its own approaches involving extended objects called strings replacing point particles, which changes the behavior of the theory at small scales in ways that might smooth out the singularity. The fuzzball model, a string-theoretic description, proposes that black holes have no interior in the conventional sense at all, that the information that fell in is encoded in a dense quantum structure at or near the horizon, and the singularity doesn't form because the geometry never gets that far. These are serious proposals. Real physicists work onto them with real mathematics. None of them has been confirmed by observation. We cannot observe the interior of a black hole. We may never be able to. Here is what I find genuinely strange about this, and I'm going to just say it plainly. We are more confident about the first 3 minutes after the Big Bang than we are about the interior of a black hole. We have a detailed, tested, observationally confirmed account of nuclear reactions that happened 13.8 billion years ago in conditions of extreme temperature and density, and we do not have a confirmed account of what is currently happening right now inside the supermassive black hole at the center of our galaxy, 4 million solar masses of sealed geometry sitting 27,000 light-years away. The far past is accessible, the close interior is not, and so the singularity sits there in the theory, a socially awkward guest at a party full of well-behaved infinities that have mostly been tamed, not removed, not explained, just predicted and named, and ringed with the acknowledgement that naming is not the same as understanding. The singularity has no address. Not because it's hard to find, but because address, the concept, the requirement that a thing exist at a locatable point in a spatial framework, belongs to the map. And the map, here, has given out. What lies past the edge of the map may be something our next theory will describe with precision and clarity. Or it may be genuinely, irrevocably outside the reach of any description that a physical theory can produce. We don't know which. The map ends. The singularity is where the map ends. And past that line for now is nothing. Not darkness, not void, not even absence. Just the edge of what the language of physics is currently able to say. Think about what light does when it leaves a surface. Any surface. The screen you might be reading from, the glass of water beside your bed, the white ceiling catching the last of whatever lamp you left on. It leaves. Without hesitation, without cost, at exactly the same speed it always travels, which is the fastest anything in the universe, is permitted to move, and it does this so effortlessly and so constantly that we've built an entire civilization on the assumption that light's travel time between nearby objects is effectively zero. You flip a switch, the room is lit, there is no perceptible lag between the departure of the photon from the bulb and its arrival at your eye. The speed is so large relative to the distances we normally navigate that it might as well be instantaneous. Near a black hole, light still travels at the same speed. That sentence sounds like it should be reassuring. It isn't quite. The speed of light, 300 million meters per second, measured locally, measured by an observer sitting next to the light as it passes, never changes. This is not a quirk of black hole physics. It is one of the foundational constraints of space-time. Special relativity. No observer anywhere measuring light passing by them will ever get a number other than that one. The constancy is absolute and it is non-negotiable, and every experiment ever conducted in the history of physics has confirmed it to a degree that makes confirmed feel like a weak word. But here is the thing that general relativity adds quietly on top of that foundation. The rate at which time passes is not the same everywhere, and if time runs at different rates in different places, slower near mass, slower deeper in a gravitational well, as we established last chapter, then light, which travels at a fixed speed relative to local time, will appear to travel slower to a distant observer whose time is running faster. Not slower locally. Locally it's fine. Locally it's always 300 million meters per second, but to someone far away, watching a photon climbing out of a deep gravitational well, the photon appears to be moving through space more slowly. Not because it is, because the time it's moving through is running slowly, and the distant observer is translating that into a velocity that comes out low. This is gravitational time dilation making itself visible into the behavior of light. The light doesn't know anything is wrong, is the thing. I keep wanting to say that, and I'm not sure it's a helpful framing, but it keeps arriving. The photon leaving the surface near a black hole, climbing outward, headed for open space, it's doing exactly what photons do, moving at c, following a geodesic, carrying its frequency, its energy, its tiny portion of the electromagnetic spectrum. It doesn't experience the well it's climbing out of, it doesn't struggle from its own reference frame to the extent that the phrase even applies to something massless. Nothing unusual is happening. But it is losing energy, measurably, verifiably losing energy as it climbs. This is gravitational redshift. As a photon climbs out of a gravitational well, it expends energy doing so, not by slowing down, but by shifting. Its frequency drops. It moves toward the red end of the spectrum. A photon that left the surface near the black hole as X-ray radiation might arrive at a distant detector as ultraviolet, or visible light, or infrared, or sufficiently close to the horizon as a radio wave, nearly drained, carrying barely a whisper of the energy it started with. The exhausted photon arriving depleted. That's the honest image. Now here is the part that requires two observers at once, and I want to hold them both in view simultaneously rather than bouncing back and forth, because the point is that they are both right and neither experience is more real than the other. Observer 1 is falling, freely falling past the event horizon following a geodesic the way we've talked about. From their perspective, time is running normally. Their watch is keeping normal time. The photon emitted by their flashlight is travelling at v in the normal speed of light. The black hole's interior, from their vantage, is a physical space they are moving through. The horizon was a location they passed, felt nothing at, and are now past. The physics around them is locally ordinary. Clocks tick, light moves, events have locations. Observer 2 is stationary, far from the black hole, watching the observer 1 fall. From their perspective, observer 1 is slowing. The light coming from observer 1 is redshifting, shifting to lower and lower frequencies as the gravitational well deepens. Observer 1's clock, as measured by the photons carrying information from it, appears to be running slower and slower. The approach to the horizon, from Observer 2's view, appears to decelerate. Observer 1 never quite arrives at the horizon. The image of Observer 1 dims, reddens, and freezes, an eternal photograph at the edge, fading toward invisibility over what in Observer 2's coordinate time is literally infinite duration. Observer 1 crosses the horizon in finite personal time. Observer 2 never sees them cross. Both of these are true. The ceiling fan in this room makes a sound on one rotation out of every 4 or 5, a faint, irregular click that I have been ignoring for months. It does it now. This is not a paradox in the sense of a contradiction requiring resolution. It is a feature. The two observers are not disagreeing about a fact, they are measuring different things. Proper time, the time elapsed on a clock carried by an observer, and coordinate time, a bookkeeping system used to label events across a region of space-time, are different objects, and general relativity is very careful not to confuse them. Observer 1's proper time to the horizon, finite. Observer 2's coordinate time to the horizon, infinite. Neither is wrong. The universe doesn't require them to agree. This is, I think, and I'll say it as an opinion because I think it is one, this is one of the places where general relativity most clearly demonstrates that our intuitions about time were always provincial. Time as a universal clock ticking the same rate everywhere was never true. It was an approximation that worked well enough at the speeds and gravitational gradients of everyday life. The underlying reality was always that time is local, personal almost. It belongs to the observer carrying the clock through their particular path through space-time. Two people can live through the same events and measure completely different amounts of time between them. The Schwarzschild radius, the distance from a non-rotating black hole's center to its event horizon, is defined by a very simple formula. 2 times the gravitational constant times the mass of the black hole divided by the speed of light squared. For the Sun's mass, this works out to about 3 kilometers. The Sun's event horizon, if it was somehow compressed to black hole density, would be a sphere 6 kilometers across. For the Earth, it's about 9 millimeters. For a stellar mass black hole of 10 solar masses, roughly 60 kilometers. These numbers sit there looking reasonable. They are not reasonable. A sphere 60 kilometers across containing 10 times the mass of the Sun, wrapped in a horizon where coordinate time stretches to infinity, and in falling observers cross in finite heartbeats, and light climbs out of it depleted and shifted and slow. 60 kilometers, near the horizon. The slowing of light has a limiting case, light emitted exactly at the horizon, or rather, the light that barely escapes, that leaves the horizon-adjacent region with just enough trajectory to head outward, takes, in coordinate time, an infinite duration to reach any finite distance from the whole. It doesn't fail to escape, it escapes. But the escape takes forever, from the outside view. Even as from the inside view, the photon is doing what photons always do, at the speed photons always travel. And light emitted from just inside the horizon doesn't escape at all. Not because it's moving too slowly, because the geometry it's moving through doesn't contain a path to the outside. Every outward geodesic curves back in. The light moves at sea, impeccably, faithfully, and goes nowhere that the outside universe can receive. The horizon is the surface where escape takes infinite time. Just inside infinite time is not enough. There's a version of this that I used to find distressing. The frozen observer, the infinite redshift, the image at the edge that never resolves. I'm not sure I find it distressing anymore. Something about it after a while starts to feel like a description of a boundary condition rather than a tragedy. The universe is not cruel about its one-way doors. It doesn't slam them. It just, and maybe this is too gentle a way to say it, it just stops at the horizon, sending information, gracefully, without announcement. The photons thin out, stretch, arrive depleted and old, and eventually there are no more of them. The message runs out before the sentence ends. That's gravitational redshift at its limit, not silence. Just the last photon arriving, too shifted, too drained, carrying a frequency so low it becomes indistinguishable from nothing. The observer inside, meanwhile, has continued. Their watch is running. Their thoughts are moving. The universe has sealed behind them, and they are now in a region of space-time that light from the outside can still enter. Information from the outside world can still reach them, but nothing from inside can reach out. Information flows in. Nothing flows out. Whatever the geometry looks like past the horizon, and we'll get to that to what the mathematics says waits further in, the photon's story ends here, at the edge, or not ends, pauses at the edge, stretched thicker, while the interior continues in a space-time that the outside universe can no longer query. The light that tried to leave is still climbing in a sense. In coordinate time it always will be, in proper time wherever it's going it's already arrived. On April 10th, 2019, at simultaneous press conferences held in Brussels, Santiago, Shanghai, Taipei, Tokyo and Washington, a photograph was shown to the world. It was blurry by the standards of what we usually call a good photograph, roughly circular, orange and amber at the brightest parts, a dark centre. The resolution was, honestly, not impressive in the way that nature photography or satellite imagery is impressive. If someone had handed it to you without context, you might have thought it was an out-of-focus shot of a lamp through fog. But it was the most distant, most massive object ever directly imaged. A black hole, the one at the centre of the galaxy Messier 87, 55 million light-years away, containing 6.5 billion times the mass of the Sun. The image wasn't blurry. That was the actual resolution limit of a telescope the size of the Earth. They had used the entire Earth. Let me say what the Event Horizon Telescope actually is, because the name suggests a single instrument, and it isn't. It is a network. 8 radio telescope facilities at the time of the 87 observation in Hawaii, Arizona, Chile, Mexico, Spain, and at the South Pole, linked together through a technique called very long baseline interferometry. Each facility recorded the incoming radio waves from M87 simultaneously, with atomic clocks, hydrogen masers, synchronizing the observations to within a fraction of a nanosecond. The data was stored on hard drives and physically flown to processing centers because the volume was too large to transmit over any network. 5 petabytes total. The South Pole data had to wait for the Antarctic winter to end before it could be collected. The image was not taken, it was reconstructed. From interference patterns, from the correlations between signals received at facilities separated by up to 12,000 kilometers. The baseline, the effective diameter of the telescope, was approximately the diameter of Earth. At the wavelength being observed 1.3 millimeters, this gave an angular resolution of about 20 microarc seconds. An angular resolution sufficient to read a newspaper in New York from Paris. Not that there was a newspaper, there was a ring of glowing gas, and a shadow, and a physics result dressed up as a picture. The cup of coffee I made an hour ago is still here. I haven't touched it. This happens more than I'd like to admit. What the image actually shows requires some unpacking, because the thing called the black hole's shadow is not the black hole. The black hole itself is, by definition, invisible. It emits nothing. It intercepts everything. It is present in the image only as an absence, a region of darkness inside the ring, and that absence is the closest we can come to a direct image of the object itself. What surrounds the shadow is a ring of plasma, hot gas accreting, falling toward the horizon in a disk. Heated to millions of degrees by the compression and friction of the infall, glows at radio wavelengths. It would glow at many wavelengths. The EHT observed it at radio wavelengths specifically because radio waves pass through the gas and dust of the galaxy with less absorption than optical light. The ring exists because there is material falling into the black hole, and that material is hot, and hot material radiates. The physics of the ring is completely separate from the physics of the shadow. Here is the part that is easy to skim over and shouldn't be. The bright ring in the image is not simply the glowing accretion disk as seen from a distance. The geometry of spacetime around the black hole is so severely curved that light from the disk takes multiple paths to reach the telescope. There is a direct image component, light from the near side of the disk, travelling relatively directly toward the observer. There is a secondary component, light from the far side of the disk, which has been bent around the back of the black hole, going over the top or under the bottom and redirected toward us. There are higher order components, light that has orbited the black hole nearly once or more than once, each successive ring thinner and closer to the edge of the shadow. These nested rings of increasingly bent light are called collectively the photon ring. Each ring is a complete image of the entire disk, wrapped around the previous one, compressed and brightened and shifted in a precise way that general relativity predicts exactly. The outermost brightest ring is the direct emission. Inside it, fainter, is the ring of light that went around once. Inside that, fainter still, the ring that went around twice. In principle, this nesting continues indefinitely, converging on the boundary of the shadow. At the innermost limit, the photon sphere, at 1.5 times the Schwarzschild radius, photons travel in circular orbits, unstable orbits. A photon can circle the black hole at this distance, technically, but any perturbation sends it either inward to the horizon or outward to eventual escape. The photon sphere is the boundary between light that escapes and light that doesn't, and its edge, projected against the sky, is what produces the sharp inner boundary of the shadow. The shadow is not the event horizon. The shadow is larger than the event horizon, about 2.5 times larger in angular size, because the curvature of spacetime bends the defining light rays outward before they project onto the sky. What we see as the edge of the dark region corresponds to photons that nearly orbited, nearly fell in, and instead just barely escaped on a trajectory toward our telescopes after a partial orbit. The image is a record of near misses. The southern part of the ring in the M87 image is brighter. This is relativistic beaming. The gas on that side is rotating toward us, its emission Doppler boosted and brightened by its motion relative to the observer. The gas on the far side is moving away, its emission dimmed. The asymmetry in brightness is not an artifact of the imaging, it is a measurement, a direct detection of rotation. The black hole is spinning. You can see it in the brightness of the ring. There's something about that image that I've turned over a lot trying to figure out what quality it has that I keep returning to it. It isn't awe, exactly. Not in the way that certain astronomical images produce awe, the pillars of creation, a galaxy collision, something visually spectacular. This image is not visually spectacular. It is, as I said, a blurry ring, amber. Small on the screen? What it is, I think, is stubborn. It has the quality of evidence that refused to be impossible. For most of human history, for all of human history until 6 years ago, a black hole was a mathematical object, a solution to equations, something whose existence we inferred from the behavior of surrounding matter, but never observed directly. The image didn't add to our certainty that black holes exist. We were already certain. What it did was something different. It made the certainty visible. It gave the mathematics a face in the loosest possible sense of that word. And the face was not dramatic or terrifying or otherworldly. It looked like a ring, a blurry ring. Evidence tends to be underdressed for the occasion. The measurements extracted from that image, and from the subsequent image of Sagittarius, a star, our own galaxy's central black hole, released in 2022, confirm general relativity's predictions in the strong field regime. The size of the shadow matched theoretical predictions, the shape matched, the asymmetry in brightness matched. Every testable claim the theory made about what an image like this should look like, at this mass, at this distance, was confirmed, not approximately, within the measurement uncertainties. A century after Einstein wrote down the field equations, an image reconstructed from radio telescope data at 12 telescopes across a planet produced a ring the size and shape the equations had predicted. The equations didn't waver. The black hole at M87's center is 6.5 billion solar masses. The solar system, our entire solar system out to the edge of the Oort cloud, is roughly 1 light-year across. The M87 black hole's event horizon is roughly 3 times that. A black hole whose edge is 3 times wider than the solar system, sitting 55 million light-years away, imaged in radio waves by 8 telescopes sharing a heartbeat. And the image is blurry. A glowing ring and a dark center, and an asymmetry that tells you the thing is spinning. That's all we got. That's all there is to get. The shadow is still there, right now, while you're listening to this. The same geometry, the same ring, the same photons orbiting and escaping and falling. 55 million light-years away, the plasma is still falling in, the accretion disk is still radiating, the photon sphere is still separating the light that escapes from the light that doesn't. The image we took was of how that looked 55 million years ago. The light left M87 when complex multicellular life was still establishing its first serious experiments on Earth. It crossed the distance, arrived at 8 telescopes on a Tuesday in April, was recorded on hard drives, flown to data centers, cross-correlated, reconstructed, calibrated, and shown to a room of people who had spent their careers working toward the moment. The room applauded. Then somebody pointed out the image looked like a donut, and for a few hours the internet couldn't decide how to feel about that, which is maybe the most human thing that happened that day. The shadow was already moving on. 55 million kilometers is a long way to carry a message, and the message when it arrived was quieter than expected. Just an orange ring, just an absence. Just the shape that space-time makes around 6.5 billion solar masses of sealed geometry projected onto a screen in Brussels on a Wednesday morning, looking for all the world like something that had been waiting a very long time to be seen. Hold your hand out flat. Now imagine. Stay with me here, this is going somewhere. Imagine that your left fingertips are very slightly closer to a massive object than your right fingertips are. Not by much. A few centimeters, just the width of your open hand. And because gravity weakens with distance, the pull on your left fingertips is, by a very small but real amount, stronger than the pull on your right. Your hand is being stretched, not painfully, not noticeably, but the geometry is there, operating on your hand right now in the gravitational field of Earth. applying a slightly different force to each part of you, depending on how far that part is from the centre of the planet. You are, at this moment, being tidally stretched, vanishingly gently, unmeasurably so at your scale. But the force exists. It is real. It is the same force that moves the oceans, and at sufficient extremes it is the force that pulls in falling matter into long thin threads before the black hole has even been reached. Same force, different magnitude. That's the whole story of this chapter, more or less. Tidal force is fussy. That's the word I keep landing on, which is probably not how it appears in any textbook. But it captures something true about its character. It isn't satisfied with pulling on a thing. It has to pull on different parts of the thing by different amounts, and it is constitutionally incapable of letting the whole object be treated as a point. It insists on the object's piece. It reaches into the interior of whatever it's working on and applies a slightly different instruction to every piece. And the more extended the object, the more pronounced the disagreement between what one end is being told to do and what the other end is being told to do. This differential, the gradient of gravitational acceleration across a finite body, is tidal force. It has nothing to do with the ocean in particular. The ocean is just large and liquid, and therefore visibly responsive to it. But the moon is tidally stretching the solid rock of Earth too, by a few centimetres per day, and the sun is doing the same, and every massive body in the universe is doing it to every other body that has any extent in space, quietly, persistently yet, regardless of whether there's an ocean to make it visible. The moon's gravity pulls on the ocean water facing it more strongly than it pulls on the centre of Earth, because that water is closer to the moon by 1 Earth radius, and it pulls on the centre of Earth more strongly than on the ocean on the far side, because the far ocean is farther by 1 Earth radius. The near ocean bulges toward the moon, the far ocean, and this is the part that used to confuse me and probably confused you too, the second bulge that nobody expects. The far ocean bulges away from the moon, because it's being pulled less strongly than the Earth's centre. So relative to the Earth, it's being left behind. 2 bulges. One towards the moon, one away. The Earth rotates under them. You get 2 high tides a day. I've known this for years and it still feels slightly wrong when I say it out loud. The far side bulge. The ocean on the opposite side of the planet from the moon, bulging outward because it's being pulled less. Tidal force working through subtraction as much as addition. The differential, not the magnitude. Now, make the gradient steeper, move the massive object closer, or make it more massive, or both. The difference in gravitational pull between the near side of an object and the far side grows, not linearly, but as the inverse cube of the distance. Closer means the gradient steepens fast, and at some point, for a sufficiently close and sufficiently massive source, the tidal force across a body-sized object is no longer gentle, no longer unmeasurable. Here is what it would feel like approaching a stellar mass black hole of, say, 10 solar masses. This is the blunt version. Your feet pointed toward the black hole are pulled more strongly than your head, not slightly. The difference at a few hundred kilometers from the horizon is enough to overcome the molecular bonds holding biological tissue together. Your body would begin to elongate, the stretching along the radial direction, toward and away from the hole, would be accompanied by a compression in the transverse directions, because tidal force conserves volume. What it stretches in one direction, it squeezes in the others. You would become longer and thinner. The process continues. The gradient steepens. The elongation accelerates. This is called spaghettification. The name is accurate. It was coined, apparently, partly in jest and then kept because nothing more formal said it better. The floor here is cold tonight. I noticed it when I got up for water earlier, and I keep noticing it. Bare feet on cold tile at this hour has a specific quality that I find difficult to describe, except that it makes everything feel slightly more real. There's a caveat, and it matters, which is that spaghettification doesn't happen at the same point for all black holes. For a stellar mass black hole, 10 or 20 solar masses, the tidal forces at the event horizon are enormous. You would be shredded well before you cross the horizon. The gradient across a human-sized object at that distance is lethal. But for a supermassive black hole, something in the billions of solar masses like an 87 star, the horizon is so far from the center that the curvature there is relatively gentle. The tidal force at the event horizon of a billion solar mass black hole is actually less than the tidal force you experience standing on Earth. You could cross the horizon of a large enough black hole and feel nothing unusual. The spaghettification weights deeper in. I find this, it's an unsettling kind of hospitality. The enormous black hole is more accommodating at its threshold. It can swallow you gently. The small one is rougher, more abrupt, as if size confers a certain courtesy. The tidal force near a black hole is, physically, the same thing operating on the Earth's oceans every day. The moon pulls, the far side lags, the differential produces a stretch, the math is identical. The tidal acceleration scales as mass divided by distance cubed. It's just that near a black hole, the mass is extreme and the relevant distances are small, and the numbers that come out are no longer measured in centimeters of ocean bulge. They're measured in forces that can disassemble matter. The moon moves about 3 to 4 centimeters farther from Earth every year because of this same process. Energy transferred through tidal interaction gradually pushing the orbit outward. The Earth's rotation slows imperceptibly as the angular momentum is exchanged. A billion years from now, the day will be longer by several hours. The moon will be farther. The tides will be weaker. The gradient persistent and fussy, reshaping the system it touches. And here is the thing I want to sit with. The thing that landed on me at some point while I was reading about tidal locking and accretion disks and binary star systems, and the various violent ways that differential gravity reshapes matter across cosmic scales. The same force. The pull on your near hand slightly stronger than the pull on your far hand. The ocean bulging on two sides of a rotating planet. The moons of Jupiter locked with one face permanently toward their planet, tidally decelerated into synchrony over millions of years. The matter in an accretion disk heating to millions of degrees as tidal stretching and compression generate friction, the infalling object drawn into a long thin thread. One phenomenon, one gradient, operating across 15 orders of magnitude of scale, from the millimeter level stretch in your hand to the cosmic restructuring of whole moons and disks and infalling stellar remnants. Gravity isn't uniform. That's the whole thing. It varies across space, and that variation, the derivative of the field, not the field itself, is what does most of the interesting work. The gradient is the story. Right now, the ocean is doing its thing somewhere. High tide, low tide, the same patient differential moving water up beaches and back down, operating on schedules determined by the orbital mechanics of a moon that has been drifting away from Earth for 4.5 billion years. Nobody is thinking about tidal force. The water just moves. The gradient just operates indifferently on whatever happens to be in its reach. Near a black hole, what happens to be in its reach is pulled into the geometry. The differential stretches infalling matter into structures that feed the accretion disk, generate the radiation we detect, produce the conditions that make black holes visible to telescopes at all. Without tidal force, there is no disk. Without the disk, there is no image. The amber ring we looked at last night exists because of the same gradient that moves the tide outside your window. The physics runs all the way through. No discontinuity, no separate laws for the extreme case and the gentle one. Just the gradient. Operating at whatever scale the situation provides. Patient and fussy and completely indifferent to the difference between an ocean and a star. Black holes are not perfectly black. That sentence took a long time to earn. Not in my reading of it. That's just a sentence. You can read it in a second, but in the physics. The physics took until 1974, and it arrived from a direction nobody was watching. And when Stephen Hawking published the calculation, the result was so unexpected that he spent time checking it for errors before he believed it himself. Black holes emit radiation, thermal radiation. The kind of radiation you'd get from any warm object. A cooling coal, a heated element, the surface of a star, characterized by a temperature, a spectrum, a measurable glow. The black hole, the object defined by the impossibility of anything escaping from within it, radiates. Not from within it. From the region just outside the horizon. Not light that fell in and came back out, something else entirely, something that requires the vacuum itself to be a participant, and the vacuum, it turns out, is very much a participant. Here is the thing about empty space that classical physics never had to worry about, and quantum mechanics cannot stop worrying about. There is no such thing as a completely quiet vacuum. The quantum vacuum, the lowest energy state of a quantum field, the closest thing the universe has to true emptiness, is not still. It is chronically restless. It fluctuates. Pairs of particles and antiparticles flicker into existence at every point in space, continuously borrowed from the energy of the vacuum itself, persisting for intervals too short to measure directly, and then annihilating back into nothing. They don't accumulate. They don't produce any net energy. They borrow and repay so quickly that the ledger stays balanced and the vacuum looks empty because the transactions happen below the threshold of what any detector can catch. This is not a theoretical convenience. It is measurable. The Casimir effect, the tiny attractive force between two uncharged metal plates placed very close together in a vacuum, exists because the fluctuations between the plates are suppressed relative to those outside them, and the difference in vacuum energy density produces a pressure. Measured, confirmed. The vacuum pushes things. The vacuum is full of something. We just can't look at it directly. Now put a horizon in the middle of it. The event horizon of a black hole does something specific and strange to the vacuum fluctuations at its surface. A pair of virtual particles flickers into existence as they do everywhere, constantly. But this time one of the pair is on the inside of the horizon and one is on the outside. They cannot reunite and annihilate. The horizon is a one-way surface. The inside particle is trapped. The outside particle, instead of annihilating back into the vacuum, becomes real. It escapes. It propagates outward into space as genuine physical radiation. The energy for this has to come from somewhere. It comes from the black hole. The black hole loses mass. Infinitesimally, absurdly slowly, we'll get to the rate, but measurably in principle. Each pair that gets split at the horizon costs the black hole something. The inside particle carries negative energy relative to an outside observer, and as it falls toward the singularity, that negative energy reduces the black hole's total mass energy by a small amount. The outside particle carries away the positive energy, escaping as radiation. The ledger balances. The black hole shrinks. I want to be honest about the virtual particle description, because I've just given you the version that appears in popular explanations, and it is useful, and it is also not quite right, in ways that matter. Hawking's actual calculation doesn't work in terms of particles at all. It works in terms of quantum fields, the underlying mathematical objects that particles are excitations of, and it shows that the curved spacetime geometry near a black hole causes the quantum field to have a different vacuum state inside the horizon than outside it. An observer far from the black hole measuring the quantum field finds it in a state that corresponds to thermal radiation at a specific temperature. This is not because particles are being created and swapped. It's because the very definition of what counts as a particle, what counts as something versus nothing in a quantum field, depends on the reference frame and the geometry of the space-time. The particle picture is a useful story. It captures the intuition. It gets the energy accounting right. But it is a story about something that is more precisely described in language that most of us, myself included, cannot fully visualize. So we use the story and we try to remember that behind the story is a calculation. The temperature of the radiation is called the Hawking temperature. For a non-rotating, uncharged black hole at all, it is proportional to 1 over the mass. Smaller black hole, higher temperature. The temperature of the radiation from a stellar mass black hole, something 10 or 20 times the Sun's mass, is approximately 10 nanokelvin, 10 billionths of a degree above absolute zero. The cosmic microwave background radiation, the thermal afterglow of the Big Bang that fills all of space, has a temperature of about 2.7 Kelvin. The Hawking radiation from a stellar mass black hole is 270 million times colder than the background. It is undetectable, completely. Not with any instrument that exists or is currently conceivable. The lamp on the desk across from me has been making a faint sound for the last hour, a sort of electrical murmur. I only notice it when everything else is quiet. For the radiation to be detectable, for the Hawking temperature to exceed the background temperature and actually produce net evaporation rather than net absorption of radiation from the environment, a black hole would need to be smaller than about 1/100th of a millimeter across, with a mass of roughly 100 million metric tons, compressed to the size of a proton. No known process in the current universe produces black holes this small. They would have to be primordial, formed in the dense conditions of the very early universe, in the first fractions of a second after the Big Bang. If such primordial black holes exist, and this is contested, there are theoretical arguments for and against. The observational evidence is ambiguous. The smallest and lightest of them might be evaporating right now, reaching the final stages of Hawking evaporation, producing bursts of gamma radiation as their temperatures climb exponentially in the final moments. No such burst has been confirmed. We haven't found one yet. Maybe they aren't there. Maybe we haven't looked in the right way. Here is the evaporation timescale for a stellar mass black hole. 10 solar masses. A black hole at the low end of what core collapse supernovae typically produce. The time for this object to evaporate completely through Hawking radiation, assuming nothing falls in and the process runs uninterrupted, is approximately 2 times 10 to the power of 74 years. Written out, 2 followed by 74 zeros. Years. The current age of the universe is approximately 14 billion years. 14 billion is 10 to the power of 10. The evaporation timescale is 10 to the 64th times longer than the current age of the universe. If you wrote the age of the universe as a single centimeter, the evaporation timescale would be 10 to the 64th centimeters long. The observable universe is about 10 to the 27th centimeters across. The evaporation timescale expressed in those terms would be 10 to the 37th times the diameter of the observable universe. I've done this calculation a few different ways, and I don't find any version of it easier to hold. It just stays large. What Hawking radiation represents, and here I'll say what I think it represents, as opposed to what it simply is the first time anyone successfully asked a question that requires both quantum mechanics and general relativity to answer. The vacuum fluctuations are quantum. The horizon is relativistic. The radiation emerges from their interaction. Neither theory alone produces it. You need the quantum field theory of the vacuum and you need the curved spacetime geometry of the horizon, and you need them in the same calculation, and when you put them there together you get a result that neither theory predicted on its own. The calculation is semi-classical. Quantum fields on a classical curved spacetime background, which is a simplification, treating the spacetime as fixed while treating the fields as quantum. A fully quantum gravitational treatment, which would require a complete theory of quantum gravity, hasn't been done. We're using an approximation that we believe captures the essential physics, the temperature it predicts, the spectrum it produces, the mass loss rate it implies. These are believed to be correct in the regime where the approximation is valid. Whether they remain correct in the final stages of evaporation, when the black hole has shrunk to near Planck scale, and the semi-classical approximation almost certainly fails, nobody knows. Two quantum mechanics and general relativity meeting at the horizon, which is exactly the kind of meeting the chapter outline promised, and which is exactly as strange as that promise suggested. The horizon is not a violent place, we established that. Nothing locally dramatic happens there. It is a geometric feature, a causal boundary, a location defined by its consequences, and yet it is precisely at the horizon. In the interplay between the quantum restlessness of the vacuum and the geometric one-way surface of the horizon, that something with a temperature emerges from something that classically has no temperature at all. Nothing pressed up against a boundary produces heat. There's a deeper strangeness here that points forward, toward the next chapter, though I want to name it now without pulling on it too hard. If the black hole radiates, and the radiation is thermal, and thermal radiation carries no information about what produced it, only temperature, only spectrum, indifferent to history, then what happens to everything that fell in? The star that collapsed, the gas that accreted, the structure and the specificity of all the matter and energy that crossed the horizon over the lifetime of the black hole. If it evaporates, and what comes out is featureless heat, then where did the information go? Where did the record go? That question, and small, plainly stated, almost easy sounding, is one of the things that has occupied theoretical physics for 50 years and is not yet resolved, and it will not be resolved tonight. And maybe that's fine. Some questions are worth carrying a while before they get answered. The warmth at the edge of nothing is real. Or at least the calculation says it is real, and the calculation has never been caught in an error. And somewhere in the radiation leaving the shrinking horizon, if the calculation is right, is the last whisper of everything the black hole ever swallowed. Whether the whisper says anything coherent is the question we take into the next chapter. When something burns, it isn't gone. The paper, the wood, the photograph, whatever you put in the fire, it becomes smoke and ash and heat and carbon dioxide and water vapour, and those products disperse, and the process looks irreversible, and in any practical human sense it is. But in physics, the transformation is technically reversible. Every molecule of smoke, every particle of ash, every photon of heat carries information about the thing that burned. The structure is scrambled beyond any realistic hope of reconstruction, but the information is there, encoded in the positions and velocities and quantum states of everything the fire produced. In principle, in the strict, idealized, this would require omniscient sense of in principle. You could run the physics backwards and recover the photograph from the ash. This is not a quirk of fire specifically, it is a fundamental property of quantum mechanics, information is conserved. The quantum state of a closed system evolves in a way that is technically reversible. Every interaction, every transformation, every physical process, the information about the initial state is preserved somewhere in the final state, however scrambled. The universe keeps records, not accessible records, not useful records, but records. This is called unitarity, and if it fails, if information is genuinely irrecoverably destroyed, then quantum mechanics, in its deepest formulation, is wrong. Now feed the photograph to a black hole. Not metaphorically. Actually drop it past the event horizon. Everything that was encoded in the physical structure of that photograph, the arrangement of silver halide crystals, the pattern of light and dark, the specific quantum states of every particle, crosses the horizon and is, from the outside universe's perspective, inaccessible. Sealed away, the black hole absorbs it. The black hole's exterior, as far as any outside observer can measure, changes in only 3 ways: mass, charge, spin. That's it. 2 identical black holes that formed from wildly different matter configurations, one from a collapsing star, one from a trillion photographs, circular from the outside identical. This is the no-hair theorem. The exterior spacetime cares only about mass, charge, and angular momentum. The details are gone. The record is sealed. Fine, except now add Hawking radiation. Add the result from last chapter. The black hole evaporates. Over cosmological timescales, it slowly loses mass to thermal radiation, and eventually, in that absurd number of years we visited, it evaporates completely. What remains is Hawking radiation, and Hawking radiation, as Hawking calculated it, is thermal, featureless, characterized only by temperature, independent of what fell in. If that's right, the photograph is gone, not inaccessible, gone. The information it contained has been destroyed by the process of black hole formation and evaporation, and the universe's record-keeping has failed, and unitarity is broken, and quantum mechanics is wrong in a way it has never been wrong before. That's the paradox. I want to be precise about why this bothers physicists in a way that goes beyond professional discomfort with unsolved problems, because I think it's easy to read information paradox as the kind of thing that sounds important but is ultimately technical, something that will be resolved by a correction to a formula. It isn't that, or at least it might not be that. If information can be destroyed, the universe is not deterministic at the quantum level. Not in the sense of classical chaos, where determinism fails in practice because initial conditions can't be measured precisely enough, in a deeper sense. A universe where information is genuinely lost is a universe where the present state does not fully determine the future and does not fully encode the past. Events happen that are, in principle, not recoverable from what came before or after. Physics becomes, at that level, genuinely non-deterministic. Not approximately, fundamentally. Hawking initially believed this was the answer, that black holes destroy information, that the universe is not, at this level, reversible. Most physicists now believe he was wrong. The argument for information conservation comes primarily from string theory's ADS/CFT correspondence, a duality discovered by Juan Maldacena in 1997, relating a theory of quantum gravity in a certain type of curved spacetime to a quantum field theory without gravity on the boundary of that spacetime. In this framework, the boundary theory is explicitly unitary, information is explicitly conserved, and if the duality is correct, the gravitational theory must be too. Black hole evaporation in the bulk corresponds to a unitary process on the boundary. Information is not lost. This doesn't tell you where the information goes. It doesn't tell you how it gets encoded in the Hawking radiation. It doesn't produce a mechanism. It says the answer must be consistent with unitarity. And here is a framework in which that consistency is enforced. The mechanism is missing, just the conclusion. There is something on the table next to me, a pen apparently that rolled off some papers, there that I keep knocking with my elbow. I've moved it twice, it is back. In 2019, 2 papers appeared, one by Ahmed Almhairi, Netta Engelhardt, Donald Marolf and Henry Maxfield, and one by Geoffrey Pennington that made significant progress on the mechanism question. They used a formula for calculating the fine-grained entropy of Hawking radiation that included contributions from regions called islands, portions of the black hole interior that, according to the calculation, should be included in the entropy accounting of the outside radiation. The result reproduced what is called the Page curve. Don Page, the same Don Page who was a doctoral student of Hawking's, pointed out in 1993 that if black hole evaporation is unitary, the entropy of the Hawking radiation should follow a specific pattern. It should start low, increase as the black hole radiates and becomes more entangled with the radiation it has emitted, reach a peak at what's called the Page time, roughly the halfway point of evaporation in terms of mass, and then decrease as the black hole shrinks and the remaining radiation begins to decode the information. The entropy should go up and then come down. A curve with a peak. Hawking's original calculation gives entropy that only goes up, monotonically increasing until the black hole is gone, at which point the radiation has enormous entropy and the black hole has ceased to exist, and the entropy has nowhere to go but into a paradox. The 2019 result reproduced the Page curve. The entropy goes up and comes down, but this is a genuine but, not a rhetorical one. The calculation uses the island formula, which is derived from replica wormhole techniques, a method involving summing over geometries in a path integral that includes contributions from wormhole topologies connecting the black hole interior to the exterior radiation. These wormholes are not the same as the Einstein-Rosen bridges we'll discuss in the next chapter. They are saddle points in a path integral, mathematical objects in a calculation. Whether they correspond to actual physical structures in space-time, whether the calculation is capturing a real mechanism, or producing the right answer through a mathematical shortcut whose physical meaning is unclear, is not settled. The Page curve is reproduced. The mechanism is not understood. The answer is there. The explanation for the answer is not. I keep thinking about this like, there's something almost frustrating about it, the way a proof by existence is frustrating when you want a construction. You've been told the treasure exists, you have not been told where to dig. There are other proposed resolutions. Firewalls. The suggestion by Almhairi, Marolf, Polchinski and Sully in 2012 that the horizon of an old black hole must be a region of high-energy radiation, a wall of fire that destroys in falling observers rather than allowing smooth crossing in order to preserve unitarity. This contradicts the equivalence principle, which says the horizon is locally unremarkable. Most physicists find the firewall proposal troubling, but cannot definitively rule it out. Fuzzballs, the string theory proposal that black holes have no interior at all, that the information is encoded in a dense quantum structure at the horizon, and that the singularity and the interior are not real features of the space-time. The information never goes inside because there is no inside. Black hole complementarity, the suggestion that information both falls in and is reflected back in the Hawking radiation, but that no single observer can access both copies, so unitarity is preserved for any given observer, even though a global perspective seems to show duplication. These are not fringe proposals. They are worked out by serious people with serious mathematics. They disagree with each other in important ways. The disagreements have not been resolved. What Hawking eventually concluded, he conceded the information paradox bet to John Preskill in 2004, handing over a baseball encyclopedia as the prize. A joke about information being retrieved from random bits was that information is probably preserved. He changed his position. The man who posed the paradox concluded, eventually, that his original answer was likely wrong. He never fully explained how the information gets out. He died in 2018, and the question is still open, and the page curve is reproduced by a calculation whose physical interpretation is disputed, and the mechanism is missing, and that is where things stand. I find this one genuinely unsettling more than most open questions in physics, and I think the reason is that it isn't just a question about black holes. It's a question about whether the universe keeps records, whether the past is encoded in the present in a way that is, in principle, complete, whether there is, written somewhere in the current state of things, a full account of everything that has ever happened. Physics has always assumed yes, not as a philosophical position, but as a working principle embedded in the structure of quantum mechanics itself. Unitarity is not one equation among others, it is a foundational property of the framework. A universe that violates it is a different kind of universe, one where things can happen and leave no trace, where the present is not a sufficient record of the past. Maybe the island's calculation is right and the information is there in the radiation, scrambled beyond recovery but present. Maybe one of the other proposals will clarify the mechanism. Maybe the resolution will come from a direction nobody is currently watching, the way Hawking radiation itself came from a direction nobody expected. The question is held open, not comfortably, not peacefully, but honestly, with the acknowledgement that held open is sometimes the most accurate description available. Some answers have the decency to arrive. This one is taking its time. In 1935, Albert Einstein and Nathan Rosen were not trying to build a tunnel through space-time. That's the thing that gets lost. The particle problem in the General Theory of Relativity, published in July of that year in Physical Review, was an attempt to get rid of singularities. Einstein found singularities philosophically offensive and mathematically suspect, and he spent considerable energy in the last decades of his life trying to construct a version of physics that didn't require them. He and Rosen looked at the Schwarzschild solution, the geometry of space-time around a point mass, which contains what we now understand to be a black hole, and instead of accepting the singular point at the center, they tried to reinterpret the geometry. They showed that the full solution could be read as two identical asymptotically flat regions of space-time connected at a throat. Two sheets of space joined at a narrow bridge. A particle in their model would not be a singularity but a geometric structure, matter as the shape of space-time rather than as stuff sitting in it. It didn't work. As a model of particles, it failed. The bridge doesn't actually eliminate the singularity in the way they hoped, and the structure they describe doesn't correspond to anything we recognize as an electron or a proton. But the bridge itself, the geometric connection between the two space-time sheets, that was real, a legitimate solution. Sitting there in the equations, accidentally profound, waiting for someone to figure out what it was actually describing. The full name for this structure is the Einstein-Rosen bridge. It became decades later a specific example of what John Wheeler would call a wormhole, a word he coined in 1957, which has since done a great deal of damage to public expectations about what physics actually permits. The cultural image of a wormhole as a traversable shortcut through space, step in here, emerge there, bypass the light speed limit, reach distant galaxies in an afternoon, comes from the word, Not from the mathematics. The mathematics is considerably less accommodating. John Wheeler and Robert Fuller showed in 1962 that the Einstein-Rosen bridge is unstable. It forms and pinches off faster than light could traverse it. A signal entering one end has no time to reach the other before the throat closes. The bridge connects two regions of spacetime, the exterior of a black hole and, in the maximally extended solution, another exterior region that may or may not correspond to anything physical, but it connects them in a way that permits nothing to pass. It is a connection that cannot be used, a door that locks itself before anyone reaches it, not traversable. This is not a soft limitation or a current technology problem. Within general relativity, traversable wormholes require matter with negative energy density, what gets called exotic matter, and whether such matter can exist in the quantities and configurations needed is, at minimum, deeply uncertain. Most physicists consider a traversable wormhole a remote theoretical possibility at best, and several serious arguments suggest it cannot be realized even in principle. The bridge is real, the shortcut is not. What the bridge is, physically, requires holding the maximal analytic extension of the Schwarzschild solution in mind for a moment. When you take the black hole geometry and extend it as far as the mathematics allows, push it out in every direction until the equations say stop, you get not one but two exterior regions, each looking like flat space-time at a distance, each connected to the black hole interior, and both connected through the interior to a second region that looks like a white hole. The time reverse of a black hole, a region from which matter can only exit, never enter. The Penrose diagram of this full solution has four regions: the black hole interior, the white hole interior, and two exterior universes. The bridge in this diagram connects the two exterior regions through the interior. It is space-like, meaning the connection exists at a moment in time, not along a path through time. You cannot travel it, but it is there. Two separate universes, or two separate regions of the same universe, touching at a throat that immediately closes. This is not a physical black hole formed by stellar collapse. Real black holes formed from collapsing stars have a different causal structure. The white hole region and the second exterior are not present. They are cut off by the infalling matter. The maximally extended solution is an idealization, an eternal black hole that has existed forever and never formed. But the mathematics of the extension is real, and real mathematics has a way of meaning something eventually. There's a lamp directly behind me that I only turned on because I couldn't see the keyboard, and it's casting a shadow across my hands that I keep noticing. This has nothing to do with wormholes. In 2013, Juan Maldacena and Leonard Susskind proposed something that, when I first read a description of it, I spent several minutes assuming I had misunderstood. Their proposal, known as ER equals EPR, is this. Einstein-Rosen bridges and Einstein-Podolsky-Rosen pairs, that is, wormholes and quantum entanglement, are the same phenomenon, described in two different languages. Two entangled black holes, maximally entangled in the specific quantum sense, are connected by an Einstein-Rosen bridge. The entanglement is the bridge is the entanglement. The geometric connection between two regions of spacetime and the quantum correlation between two systems are not analogous things or related things. They are, in this conjecture, the same thing. The implications, if this is right, are large and strange and not fully worked out. The geometry of space-time, the fact that two regions are connected, the fact that there is a throat between them, emerges from quantum entanglement. Space-time connectivity is entanglement, which means, in some versions of this picture, that space-time itself, the geometric structure we've been talking about for 9 chapters, the thing that curves and bends and tears at singularities, is built from quantum correlations between things. The geometry comes from the entanglement, not the other way. This is a conjecture. It has mathematical support. It was developed in the context of ADS/CFT, the same framework that bears on the information paradox, and the specific case of 2 entangled black holes connected by an eternal bridge has been studied extensively, and the duality holds up under scrutiny. But it has not been proven in the general case. Its physical interpretation is contested. What it means for real black holes, formed from collapsing matter, in an asymptotically flat spacetime rather than the anti-de Sitter spacetime of the ADS/CFT framework, this is not settled. Maldacena has said that the conjecture suggests spacetime itself is a kind of emergent phenomenon, that the smooth, continuous geometry of general relativity, the stuff that curves around mass, the stuff that tears at singularities, the stuff we've been living inside for this entire conversation, is not fundamental. It emerges from something more primitive, from quantum information, from entanglement structure. If that's right, the question of whether a black hole can destroy spacetime gets considerably more complicated. Spacetime in that picture isn't the kind of thing that gets destroyed. It's the kind of thing that gets disentangled. In November 2025, a paper published in Physical Review Letters by Javier Magan, Martin Sacchietta, and Brian Swingle described what they called Einstein-Rosen caterpillars. The interior of a typical black hole, not the idealized eternal black hole of the maximally extended solution, but a realistic black hole in a typical quantum state, contains, according to their calculation, not a single symmetric bridge but a sprawling irregular network of wormhole-like structures, dense, chaotic, entanglement-shaped. The interior geometry is not smooth or simple. It is complex in the technical sense. Its complexity grows over time as the black hole evolves, the interior structure becoming more tangled, the wormhole network longer and more irregular. The length of the wormhole network inside a black hole, in this picture, increases as the black hole area, not the spatial extent of the black hole, the complexity of its interior quantum geometry. The bridge isn't a tunnel. It's something more like... Actually, I keep reaching for comparisons here and pulling back from them, because the structure they describe doesn't have a good everyday analogue. It's a high-dimensional geometric tangle whose length is a measure of quantum complexity. The image of a wormhole as a clean tube connecting 2 points survives science fiction. The mathematics has moved somewhere considerably stranger. What is worth sitting with, I think, what I keep returning to about the Einstein-Rosen bridge and everything that has grown from it, is that it started as an accident. Einstein and Rosen were trying to do something else. The bridge appeared as a feature of the solution they were analysing, not as something they were looking for. They looked at it, tried to use it for their purposes, found it didn't serve those purposes, and published the mathematics anyway. And then, 90 years later, the mathematics turned out to be a word in a vocabulary that physicists are still learning to read. The bridge connects, in ways that Einstein certainly never considered, to quantum entanglement, to the structure of space-time, to the information paradox, to the question of whether geometry is fundamental or emergent. The accidentally profound thing keeps producing consequences. The bridge is probably not traversable, almost certainly not. The corridor that science fiction built from it is not supported by the mathematics. But the mathematics itself, the connection, the throat, the geometry of 2 regions touching, is serious. And the question of what it means, whether the bridge and entanglement are really the same thing, Whether spacetime is built from quantum correlations that can in principle be disrupted, these are open, being worked on, argued about in papers and at conferences and in the kind of late-night conversations that physicists have when they stop performing certainty. The bridge appeared in an equation in 1935. It hasn't stopped meaning things since. Everything that forms from a collapsing cloud of gas is already spinning. Not because spinning is required, not because some rule mandates it at the start, but because the gas cloud, before it collapses, almost never has perfectly zero angular momentum. It drifts. It moves through a galaxy that is itself rotating, perturbed by passing masses, nudged by asymmetries in the distribution of nearby matter. And when a rotating cloud collapses under its own gravity, angular momentum is conserved. The rotation doesn't dissipate into the collapse, it compresses into it. What was a diffuse, slow rotation spread across a volume of gas becomes, as that volume shrinks by many orders of magnitude, a fast rotation concentrated into a tiny remnant. Ice skaters know this. Pull your arms in and you spin faster. The physics is identical, the scale is not. A collapsing stellar core that begins with even a small rotation will end with an extremely fast one. Neutron stars, have the remnants of less massive collapses, have been observed spinning hundreds of times per second. Hundreds of complete rotations per second. A sphere roughly 20 kilometers across, the mass of the Sun, rotating fast enough that its equator moves at a significant fraction of the speed of light. The spin is not incidental to what the object is, it is structural. It shapes the space-time around it. It is inherited from the cloud, amplified by the collapse, and it does not go away. For a black hole, the situation is the same, more so. The geometry of space-time around a rotating black hole was worked out by Roy Kerr in 1963, a year that deserves more acknowledgement than it typically gets in popular accounts of black hole physics. The Schwarzschild solution, the geometry of a non-rotating black hole, had been known since 1916, but almost all real black holes rotate. The Schwarzschild solution is an idealization, useful and tractable and genuinely important, but describing something that probably doesn't exist in nature in pure form. Kerr's solution described the general case. It took nearly 50 years after general relativity was formulated to find it, and when Kerr presented it at a conference in 1963, several attendees reportedly left before he finished speaking. They didn't recognize what it was. The Kerr metric, the mathematical description of space-time around a rotating mass, is considerably more complicated than Schwarzschild's. The rotation breaks the spherical symmetry. The geometry is axisymmetric instead, symmetric around the rotation axis, but not around any other axis. Things are different at the equator than at the poles. The singularity is no longer a point but a ring oriented in the equatorial plane, and instead of one horizon there are two horizons, an outer event horizon and an inner Cauchy horizon. The outer horizon is the one-way surface we've spent the most time with, the surface past which outward geodesics no longer exist. The inner horizon is a different kind of boundary, associated with problems of determinism and instability that make most physicists suspect it is altered or destroyed in realistic scenarios by falling radiation. These two surfaces exist at different radii, both dependent on the black hole's mass and spin, converging to a single horizon at maximum spin and separating increasingly as spin decreases toward the Schwarzschild limit of zero. The ring singularity sits in the equatorial plane. It can, in the mathematics of the maximally extended Kerr solution, be avoided by an infalling traveller approaching from the polar direction. Whether this mathematical possibility corresponds to any physical reality is contested. let's say contested, and move on. The thing about the Kerr geometry that I find most genuinely difficult to absorb is not the dual horizons or the ring singularity. It is something that happens outside the outer horizon entirely. Something in the space you could, in principle, enter and exit. The thing called frame dragging. A rotating mass drags space-time around with it. Not metaphorically. Not as an analogy for something else. The rotation of the mass physically affects the geometry of the space-time in its vicinity, inducing a rotation in the geometry itself. Space-time near a rotating black hole is not a neutral container in which the black hole happens to be spinning. Space-time is spinning too. The geometry has been twisted in the direction of the black hole's rotation, and the twist extends outward, weakening with distance but never fully vanishing. This was predicted by Einstein's field equations and confirmed experimentally. Gravity Probe B, a NASA mission, launched in 2004, carried gyroscopes in orbit around Earth and measured the tiny precession caused by Earth's rotation dragging the local space-time around it. The measurement matched the prediction to within a fraction of a percent. Earth's effect is tiny. A rotating black hole's is not. The back of my neck is stiff in the way it gets when I've been sitting at the wrong angle for too long without noticing. Near a rapidly rotating black hole, the frame dragging becomes extreme. Imagine, and I want to be careful here because the fluid analogy I'm about to use is useful but limited. Imagine space-time as a medium with a current. Not a current like water, not a physical substance flowing, but a geometric tendency. The local standard of not rotating has itself been set into rotation by the mass. An object that fires its engines continuously to hold itself perfectly still with respect to distant stars, zero rotation, zero orbital motion, just hovering, finds, close enough to a Kerr black hole, that it cannot do this. The engines aren't powerful enough. The local geometry's definition of non-rotating has drifted from the distant star's definition of non-rotating. The object is dragged, and resisting the drag requires infinite force at the boundary of a specific region. That boundary is the ergosphere. The fluid analogy breaks down here, which I want to say plainly. Space-time is not a fluid. It doesn't have viscosity or pressure or turbulence in the physical sense. The current metaphor captures the directional bias imposed by rotation, the way nearby space has acquired a preferred orientation, but the mechanism is geometric, not hydrodynamic. The equations are Einstein's, not Navier-Stokes. I've found the metaphor useful, and I've also found the moment where it misleads, and that moment is roughly here. The ergosphere is a region surrounding the outer event horizon of a Kerr black hole, shaped like an oblate spheroid, flattened at the poles, bulging at the equator, touching the event horizon at the poles, and extending beyond it at the equatorial plane. Its outer boundary, called the static limit or ergo surface, is defined precisely as the surface at which the frame dragging has become so severe that no object, regardless of how powerful its engines, regardless of what it does, can remain stationary with respect to the distant stars. Inside the ergosphere, rotation is not optional. This is the sentence I kept building toward, and I want to leave it alone for a moment. Inside the ergosphere, objects are not pulled toward the black hole in the way matter is pulled toward the event horizon. They can still escape. They can still move outward, exit the ergosphere, return to open space. The ergosphere is outside the event horizon. It is not a trap in the classical sense, but it is a region where stillness has been abolished, where the local geometry, the structure of space-time itself, is rotating with sufficient velocity that no physical object can stand against it. The ergosphere's definition of not moving requires, from the perspective of the distant universe, moving in the direction of the black hole's rotation, always, without exception. I keep trying to think of a comparison for this, and the one I keep almost reaching for isn't right, so I won't use it. The honest description is, it is a region of space where 1 degree of freedom has been taken from you. Not by force, by geometry. The same way the interior of the event horizon removes your ability to move outward in space. That direction bends into time. The ergosphere removes your ability to be rotationally still. Not your ability to resist rotation against a torque. Your ability to not rotate at all. The geometry has a direction. Inside the ergosphere, you participate in it. Remo Ruffini and John Archibald Wheeler named this region the ergosphere in 1971, from the Greek ergon, meaning work, because they recognized it as a region from which work could be extracted. Energy could be taken from the black hole's rotation by exploiting the geometry of this region. We'll spend the next chapter in that process, but right now the name is what I want to sit with. The ergosphere, the sphere of work. A region defined by what it does, what it requires, what it takes from any object that enters it. Most black holes in the universe are probably rotating, not at maximum spin, the theoretical limit where the two horizons coincide and the ergosphere reaches its maximum extent, but significantly. Some astrophysical black holes have been measured, through X-ray observations of their accretion disks, to be spinning at substantial fractions of the maximum rate. The geometry around them is not the Schwarzschild's clean spherically symmetric solution. It is Kerr's asymmetric, dragging, ergosphere-bearing solution, and the difference is not cosmetic. The accretion disk around a rapidly spinning black hole behaves differently than one around a non-spinning black hole. Material can orbit more stably at smaller radii. The innermost stable circular orbit shrinks as spin increases, allowing matter to fall deeper before being captured, generating more energy in the process. The jets, the relativistic beams of material that some black holes produce, extending millions of light years into intergalactic space, are powered, at least in part, by the rotational energy of the black hole itself, extracted through electromagnetic processes related to the same ergosphere, physics that Penrose identified. The rotation is not incidental. It is the energy source. It is built into the geometry. It was inherited from a gas cloud that drifted through a spiral galaxy and happened billions of years ago to have a slight preferential motion in one direction rather than another. That slight drift became the ergosphere. That slight drift became the jets. That slight drift became a region of space-time where nothing can stand still. The geometry remembers everything the matter that made it ever did. Roger Penrose noticed something in 1969 that should not have been there. He was working through the mathematics of the Kerr geometry, the rotating black hole solution we spent the last chapter inside, and he found that within the ergosphere, a particle's energy, as measured by a distant observer, is permitted to be negative. Not small, not approximately zero, negative. A particle moving in a specific way, counter to the black hole's rotation, in the right part of the ergosphere, carries a value for energy that an observer at a safe distance would measure as less than nothing. This sounds like a bookkeeping error. It isn't. In flat spacetime, energy cannot be negative. A particle at rest has its rest mass energy, which is positive. A moving particle has kinetic energy on top of that, also positive. You can make the total smaller by removing kinetic energy, but you bottom out at the rest mass. Zero is not reachable for a massive particle, and negative is simply not a category available to the math in ordinary space. But the ergosphere is not ordinary space. Inside it, as we established, The geometry itself is rotating. The local standard of rest has been dragged into motion, and in that drag geometry the relationship between a particle's motion and the energy a distant observer assigns to it gets reshuffled. Counter-rotating motion opposing the black hole's spin, which is already nearly impossible to sustain in the ergosphere, can produce for the right trajectory a negative energy value that is not an error in the calculation. It is a feature of the geometry. Penrose then asked the obvious next question. If negative energy particles can exist in the ergosphere, what happens if you send something in that splits? The mechanism is this. An object, a clump of matter, anything with mass, enters the ergosphere intact. Inside it breaks apart. Two pieces. The split is arranged so that one fragment takes a trajectory that gives it negative energy as measured from far away and falls inward, crosses the event horizon, disappears into the black hole. The other fragment takes a different trajectory, one with positive energy, and escapes outward, exits the ergosphere, flies out into open space. Now do the accounting. The original object had some energy before it entered. Positive, normal, the rest mass plus whatever kinetic energy it carried in. After the split, the fragment that fell in had negative energy. The fragment that escaped carried positive energy. Conservation of energy means the escaping fragment's energy equals the original object's energy minus the infalling fragment's energy. The infalling fragment's energy was negative. Subtracting a negative number adds. The escaping fragment carries more energy than the entire original object started with. Something came in, something different came out. The something that came out has more energy than the something that came in. Where did the extra energy come from? It came from the black hole's rotation. The infalling fragment, carrying negative energy, reduces the black hole's total mass energy by a small amount when it crosses the horizon. But the black hole's angular momentum also decreases. The counter-rotating fragment has been carrying negative angular momentum too, and the black hole absorbs it, spinning down slightly. The black hole loses rotational energy. That loss is the source of the energy the escaping fragment gained. This is the Penrose process. Energy extracted not from fuel burning, not from matter annihilating, not from any chemical or nuclear reaction, from the rotation of space-time itself, from the geometric spin of the black hole, encoded in the Kerr metric, inherited from whatever collapsed to form it. The process reaches into the structure of the geometry and withdraws something. The maximum efficiency for a single extraction event, the most energy you can pull out relative to the mass you put in, is about 20.7% for a maximally spinning black hole. This sounds modest until you remember what it's being compared to. Nuclear fission releases less than 1% of rest mass energy. Nuclear fusion, the process powering stars, gets up to about 0.7%. The Penrose process, extracting rotational energy from geometry, beats the Sun's engine by a factor of 30. 20.7% of the rest mass of whatever you send in comes back out as extractable energy. The geometry paid for it. My desk chair makes a noise when I shift forward. I shifted forward. In 1971, the physicist Yakov Zeldovich pointed out that the Penrose process was an example of a broader phenomenon, rotational superradiance, and translated it from black holes to something more testable. A rotating absorbing cylinder, he showed, should amplify certain electromagnetic waves in the same way the ergosphere amplifies particles. The energy comes from the rotation in both cases. The mechanism is the same geometry dressed in different clothes. This was confirmed experimentally in 2020 using acoustic waves and a rotating absorber in a laboratory. Not a black hole, not even close to a black hole, a cylinder, spinning in a room. The waves came out louder than they went in. The Penrose process, in a manner of speaking, has been demonstrated on a tabletop. Now here is the part that I find, I'm going to say, genuinely surprising even after thinking about it for a while. The part that keeps catching me. The black hole doesn't cooperate with this process. It doesn't have a choice. The geometry simply allows it, and the energy accounting simply works out, and that's the whole mechanism. There is no agent here, no reaction, no pushback from the black hole as its spin is reduced. The rotational energy is accessible because the ergosphere exists, and the ergosphere exists because the black hole is spinning, and the spinning is a geometric property of the space-time. Draining it doesn't require the black hole to do anything. It requires only that the geometry permits certain trajectories, and the geometry does. There is a limit. Penrose showed this clearly. You cannot spin the black hole down indefinitely. As the rotation decreases, the ergosphere shrinks. The outer boundary of the ergosphere approaches the event horizon. At zero spin, the Schwarzschild limit, the ergosphere vanishes entirely. There is no longer a region where negative energy trajectories exist. No more Penrose process. The source is gone. You have extracted everything extractable, and what remains is a non-rotating black hole that cannot be drained further by this mechanism. The total energy extractable, across all possible extraction events, spinning the black hole from maximum rotation down to zero is, for a maximally spinning black hole, about 29% of its total mass energy, not 20.7%. That's the single event maximum. The cumulative maximum draining the spin completely is 29% of the entire rest mass. In energy terms, for a black hole of 10 solar masses, 10 solar masses is roughly 2 times 10 to the 31st kilograms. 29% of that times the speed of light squared. The number is large enough that I'd rather not write it out and pretend the writing makes it real. Astrophysicists believe the Penrose process, or more precisely electromagnetic versions of it, where magnetic fields threading the ergosphere do the extracting rather than splitting particles, is responsible for powering the relativistic jets produced by some black holes. The jets that extend millions of light years, the ones visible from other galaxies, material flung outward at significant fractions of the speed of light carrying enormous energy, produced by a process that reaches into the spin of a black hole and pulls. The specific mechanism is called the Blandford-Znaeck process, proposed in 1977, and it operates through the interaction of the rotating space-time with magnetic fields threading the ergosphere and the accretion disk. The mathematics is considerably more involved than the simple particle splitting picture Penrose described, but the energy source is the same, the rotation, the geometry. A quasar, one of the most luminous objects in the observable universe, outshining entire galaxies of hundreds of billions of stars from a region not much larger than the solar system, is powered at its heart by this, by the spin of a black hole and the geometry that spin creates and the process that geometry permits. The ergosphere is not decorative. What the Penrose process reveals, I think, and this is an opinion about what the physics means, rather than a description of what it says, is that rotation is a form of stored energy in a way that has no analogue in non-relativistic physics. A spinning top has rotational kinetic energy, yes, but the energy is in the motion of the top's material. You can extract it by applying friction, slowing the material down. The top is the thing spinning and the energy is in the top. A Kerr black hole is different. The rotation is a property of the space-time geometry. There is no top, there is no spinning material at the horizon. The geometry has spin as a parameter, and that parameter encodes a reservoir of energy that can be drained by sending matter into the ergosphere in the right way. The energy is in the shape of space and time, not in the motion of any stuff, and it can be spent, slowly, event by event, or in principle more rapidly. The geometric spin decreases, the ergosphere shrinks, the shape changes. Somewhere in the idea that space-time has a geometry and that geometry has energy and that energy can be extracted and depleted, is something that feels important to carry forward. Not because the Penrose process directly answers the question this series is building toward, but because it establishes something quietly significant. Space-time is not just a stage. It is not just a container for things that have energy. It has energy of its own, stored in its shape, accessible under the right conditions. It can be drawn down. Whether it can be destroyed is the question still ahead. But the fact that it can be spent, that the geometry participates in the energy budget of the universe as a source, not just a structure that changes what destruction would even mean. Most galaxies have one, a supermassive black hole at the center, millions or billions of solar masses sitting in the nucleus, shaping the dynamics of the stars and gas around it through gravity that operates across thousands of light years. The Milky Way has one, Sagittarius. A star 4 million solar masses, imaged in 2022, sitting 27,000 light-years from where you are right now. Messier 87 has one 6.5 billion solar masses, the first black hole ever photographed. Almost every large galaxy we've examined in sufficient detail has revealed one at its core. Galaxies also merge, not quickly, not violently in any human sense of the word. A galaxy merger takes hundreds of millions of years and involves so much empty space between stars that actual stellar collisions are rare. What happens is a slow gravitational entanglement, two systems drawn together, their shapes distorting, tidal streams of stars being pulled out into long arcs, the whole structure gradually settling into a new combined form over timescales that make geology look hasty. And when two galaxies merge, the supermassive black holes at their centers begin moving toward each other. The early stages of this process are well understood. The two black holes, each carrying its own mass and history and spin, sink toward the combined center of the merged galaxy through a process called dynamical friction. They lose energy to the stars and gas around them, scattering material that carries away momentum. Slowly, the way a large object moving through a crowd loses speed by deflecting the crowd. This phase takes hundreds of millions of years. The black holes spiral inward, their separation decreasing from tens of thousands of light years to tens of light years to eventually scales where something else takes over. At separations of roughly a parsec, about 3 light years, the supply of stars on orbits that can efficiently carry away more angular momentum starts to run out. The black holes stall. This was, for decades, a theoretical problem called the final parsec problem, a gap in understanding how the black holes could get close enough for gravitational wave emission to take over the inspiral. Recent simulations and observations suggest the gap is bridged by gas dynamics, by the non-spherical distribution of stars in real galaxies, by various mechanisms that don't operate in the idealized models where the problem first appeared. Real galaxies are messier than the models. In this case, the mess helps. Eventually, and this word is doing significant work here, eventually meaning somewhere between tens of millions and billions of years after the galaxies began merging, the two black holes are close enough that their orbital decay is dominated by gravitational wave emission. They orbit each other. Two supermassive objects, each warping spacetime severely in its vicinity, orbiting a common center, and with each orbit radiating energy outward as gravitational waves. Ripples in the curvature of spacetime itself, propagating outward at the speed of light. The energy lost to these waves comes from the orbital energy of the pair. The orbit shrinks, the black holes move closer. The orbital period decreases. Closer means faster, means more gravitational wave power, means faster in a spiral. This is a runaway process, in slow motion, across millions of years. The gravitational waves produced during this phase, the long-in-spiral phase of a supermassive binary, have frequencies far too low for the LIGO detectors that found stellar mass black hole mergers. LIGO is sensitive in the range of tens to thousands of hertz. A supermassive binary in the later stages of in-spiral produces waves at frequencies of millihertz or below, wavelengths of millions of kilometers, periods of minutes to hours. To detect these, you need a detector with an arm length comparable to the wavelength. LISA, the Laser Interferometer Space Antenna, a European Space Agency mission scheduled for launch in the 2030s, will use 3 spacecraft separated by 2.5 million kilometers, forming a triangle in space measuring the stretching and squeezing of the distance between them as gravitational waves pass through. 2.5 million kilometers. The detector is larger than the Sun. The rain has started again outside, the same fine rain as before or different rain. It's impossible to know. I want to stay with the in-spiral for a moment because I think we move past it too quickly in the standard telling, anxious to get to the merger. 2 objects, each potentially billions of solar masses, orbiting each other across a separation that is shrinking. The orbital period at the late in-spiral stage, when the separation has closed to say a few hundred Schwarzschild radii, might be years. Years per orbit. And the whole system is losing energy, tightening, the orbit decaying with each pass. 1 billion years of this. The same 2 objects passing each other again and again, each pass bringing them slightly closer, each pass radiating slightly more energy into the space-time around them. No event horizon has been reached. Nothing has been swallowed. Just 2 enormous sealed geometries orbiting, tightening, patient. I find this, and I'll say it simply, I find this more affecting than the merger itself. Not because the merger isn't significant, because the in-spiral is so long and so indifferent to its own outcome. It doesn't know it will end in merger. It is just physics proceeding, millions of years of proceeding. The merger itself happens fast. After the long in-spiral, after whatever multiple of millions of years the specific system required, the final plunge takes milliseconds. The 2 event horizons approach, deform, touch, merge into a single distorted horizon that oscillates and radiates gravitational waves furiously as it settles into the shape of a new, larger Kerr black hole. This settling, the ring down, is itself a source of gravitational waves, at a frequency determined by the mass and spin of the remnant, decaying exponentially as the geometry relaxes into its new stable form. The energy released in gravitational waves during the final merger and ring down of 2 supermassive black holes can exceed the total energy output of all the stars in the observable universe combined. For a fraction of a second. That sentence exists. I've written it before in notes and I still don't know what to do with it after it's been written. The gravitational waves from these mergers are not like sound or light. They are not vibrations in a medium. They are the medium itself vibrating, the metric of space-time oscillating, the distances between points in space literally changing as the wave passes. A gravitational wave passing through you right now. And there are gravitational waves passing through you right now from various sources, though at amplitudes so small they are effectively 0, would stretch you very slightly in one direction and compress you in the perpendicular direction, and then reverse at whatever frequency the wave carries. The waves from a supermassive merger would do this to everything in their path, including the space between galaxies, including the large-scale structure of the universe, including any detector sensitive enough to hear them. Pulsar timing arrays, networks of millisecond pulsars distributed across the galaxy, used as natural clocks whose timing residuals reveal the passage of gravitational waves, have recently found evidence for a gravitational wave background at the relevant frequencies. A hum, not from one merger but from many, the accumulated signal of supermassive binary mergers across cosmic history, overlapping, blending into a stochastic background that permeates the universe. We are sitting inside a gravitational wave background produced by billions of years of black hole mergers. The universe has been having these collisions since long before there were eyes to watch them. The space-time has been ringing. There is a pair of supermassive black holes, likely more than one, probably many, that are right now in their inspiral phase, orbiting, tightening, radiating, patient in the way that only things operating on geological and cosmological timescales can be patient, which is to say, not patient at all in any experiential sense. Just continuing, because continuing is what physics does. Some of those pairs are in a late stage. Separation below a parsec, gravitational wave emission already significant. The final plunge perhaps mere millions of years away. Millions of years is soon in this context. The merger, when it happens, for any specific pair, takes milliseconds. Everything before that is the story. The galaxy collision that started the clock hundreds of millions of years before, the dynamical friction phase. The final parsec crossed somehow, the long in spiral, orbit by orbit, each one a little tighter, and then the milliseconds when it resolves. Two seal geometries become one seal geometry, the horizons merge. The ring down quiets. The new black hole, larger, carrying the combined mass minus whatever was radiated away, spinning at whatever rate the merger dynamics produced, settles into its Kerr solution and sits there, changed, finished with the process that made it. The gravitational waves from that millisecond of merger travel outward at the speed of light. They pass through galaxies and gas and the large-scale structure of the universe. They carry in their oscillation pattern the record of the masses and spins and orbital geometry of the pair that produced them. In principle, if a detector intercepts them and is sensitive enough, everything about that merger can be read from the wave. Lisa, if it launches and operates as planned, will hear these, not one but dozens per year, perhaps more, supermassive mergers across cosmic time, their signals arriving at a triangle of spacecraft 2.5 million kilometers to a side, shifting the distances between them by amounts smaller than an atomic nucleus. The pair right now, wherever it is, doesn't know. It will be heard. It's just orbiting, tightening. Each pass a little faster than the last, the radiation carrying away the energy that used to be the orbit, the seal geometries drawing toward each other across a distance that is still enormous by any ordinary measure, but is, by the standards of what it will become, nearly nothing. The universe is full of these quiet countdowns. Most of them will never be observed. Some will be by detectors that don't yet exist, recording the waves from mergers that will happen long after anyone reading this is gone. The inspiral continues regardless. The space-time rings whether or not anyone is listening. Start with something simple. A table exists, it occupies space, it persists through time. If you hit it, it pushes back. If you put something on it, the something stays there. The table is a physical object with properties, mass, rigidity, temperature, the ability to interact with other physical objects in specific and predictable ways. Nobody seriously debates whether the table is real. It is plainly, unambiguously a thing. Now ask the same question about the space the table is sitting in. This sounds like a philosophy question, the kind that tends to make physicists impatient. And for most of the history of physics, it was handled with something close to impatience. Space is where things are. Time is when things happen. Together, they form the backdrop against which physics plays out, the stage, the neutral container, the coordinate system you write your equations in. Real in a practical sense, obviously, the way the stage is real when a play is being performed, but not a physical thing in the way the table is a physical thing. Not something that can be hit, or measured, or changed by what sits in it. This view is not wrong exactly. It works for enormous ranges of physical problems. It is just, from the standpoint of general relativity and everything built on it, willfully naive about what the equations are actually saying. General relativity does not treat spacetime as a container. It treats spacetime as a field, a physical field with its own degrees of freedom, its own dynamics, its own energy content in some regimes. Mass curves it. Moving mass produces waves in it. Those waves carry energy and momentum across the universe. The field has a state at every point, and that state evolves according to equations, and the evolution affects everything inside it, and everything inside it affects the evolution. This is not a restatement of the obvious fact that gravity is a force. It is a claim about the nature of space-time itself. The geometry is not fixed, it responds. It is part of the physical system, not the coordinate system you use to describe the physical system. When you write down Einstein's field equations, you're writing an equation of motion for space-time, for the metric, the mathematical object that describes the geometry. Just as surely as Newton's second law is an equation of motion for a particle. Space-time in general relativity is dynamical. It moves, it changes, it has its own physics. The question is whether this is real or just a useful mathematical framework. And here is where the experiments become important, because the experiments are not ambiguous. Gravitational waves, which LIGO first detected in September 2015 from two merging stellar mass black holes, are not waves propagating through space-time the way sound propagates through air. They are waves in space-time. The space-time metric itself oscillating, the geometry of space rippling, the actual distances between points in space changing as the wave passes. The detectors measure this directly. 2 4-kilometer arms at right angles, laser light bouncing between mirrors, the interference pattern shifting by less than 1,000th of the width of a proton as the wave stretches one arm and squeezes the other. What LIGO measured was the geometry changing, not something moving through the geometry itself. My shoulders ache tonight in a specific way that means I've been hunched without noticing for too long. The energy content of gravitational waves confirms this further. When two black holes merge, as in that first LIGO detection, two black holes of roughly 36 and 29 solar masses producing a remnant of roughly 62, the mass of the remnant is less than the sum of the original masses. About 3 solar masses worth of energy was radiated away as gravitational waves in roughly 1/5 of a second. 3 solar masses, gone, converted to ripples in the metric and carried off at the speed of light. That energy was real. It came from somewhere. It was stored in the geometry of the two black hole system, Ollie, in the orbital dynamics, in the interaction of their space-time geometries, and it left as geometry waves. If space-time were merely a container, where did that energy live? Containers don't have energy. Containers don't radiate. The 3 solar masses did not come from the matter. Both black holes crossed their horizons intact. The energy came from the space-time geometry of the system. The geometry had energy. The geometry spent it. The frame dragging we discussed in the rotating black hole chapters is another piece of this. Gravity Probe B's gyroscopes precessed not because a force was applied to them, but because the geometry of space-time around the rotating Earth was itself rotating slightly, and the gyroscopes, following their local geodesics faithfully, were carried around with the geometry. The geometry moved. The gyroscopes moved with it. A thing that is merely a coordinate system cannot rotate. A coordinate system doesn't drag anything. Something physical dragged those gyroscopes. Time dilation, clocks running at different rates at different altitudes, measured to extraordinary precision by atomic clocks at different heights, required as a correction in GPS satellites, reflects the geometry having a physical state that varies from place to place. The metric is different at different heights. Clocks measure proper time along their world lines, and proper time is determined by the metric, and the metric is a physical field that has a specific value at each location. Clocks at different altitudes run at different rates because they are in different physical states of the space-time field. The field is physical, the state is physical. This is not a new claim. It is what general relativity has been saying since 1915. What has changed over the last century is the accumulation of evidence so thorough and so varied that the physical reality of space-time as a dynamical field is no longer seriously contested among physicists who work with it. Gravitational waves, frame dragging, gravitational lensing, time dilation, the expansion of the universe, which is not galaxies moving through space but space itself expanding, the metric changing at cosmological scales, carrying galaxies with it the way raisins in rising bread are carried apart, not by moving through the dough, but by the dough growing between them, the metric expanding, the geometry itself doing the thing. All of it points to the same conclusion. Space-time is not a stage, it is not a container, it is not a neutral coordinate system, it is a physical thing with a geometry that changes, carries energy, propagates waves, drags gyroscopes, dilates time, expands at cosmological scales, and curves in the presence of mass. It is a thing. Now, here is the complication I want to place carefully, because it matters for everything that follows. There is a serious possibility, not a fringe idea, a mainstream research direction with significant mathematical support, that space-time, despite being a physical thing, is not a fundamental one. The ER equals EPR. Conjecture we discussed suggests that the geometry of space-time may emerge from quantum entanglement. The ADS/CFT correspondence, which has been productive in theoretical physics for nearly 30 years, describes gravity in a bulk spacetime as equivalent to a quantum field theory without gravity on the boundary of that spacetime, suggesting that the bulk geometry is, in some sense, encoded in the boundary quantum theory. Spacetime in these frameworks is emergent. It is what you get when quantum degrees of freedom organize themselves in certain ways. It is real, the table analogy holds, but it is not the bottom layer. If this is right, then spacetime is physical in the way that temperature is physical. Temperature is real. It does things, you can measure it, it burns you, it governs the behavior of gases and liquids and solids, but temperature is not fundamental. It is an emergent property of the collective behavior of many particles. You cannot have a single particle temperature. Temperature is a thing, but it is the thing made of other things. Space-time in the emergent picture might be similar, real, dynamical, physical, and made of something else, something we don't yet have a complete theory of. Why does any of this matter for the question this series has been building toward? Because the question, can a black hole destroy spacetime, is only grammatically coherent if spacetime is the kind of thing that can be destroyed. If spacetime is a neutral container, the question doesn't pass. You can't destroy the stage without destroying everything on it. And there's no force that acts on the stage itself, only on the players. The question would be malformed. But if spacetime is a physical field, dynamical, energetic, capable of carrying waves and being curved and being changed, then the question becomes real. Not metaphorical, not rhetorical, actual. What happens to the field at the singularity? What happens to the geometry when the curvature diverges without bound? Is there a sense in which the physical field fails? Is there a sense in which something that was spacetime stops being spacetime? These are physics questions, not philosophy questions. Questions with potential answers in quantum gravity, in whatever theory comes after general relativity, in the mathematics we are still building. I keep saying the question is being built toward, and here, finally, is the sentence the whole chapter was preparing. Can a black hole destroy spacetime itself? We now know what we're asking. We know we're asking about a physical thing. We know that thing is dynamical and real and possibly emergent and certainly not eternal and unchangeable and inviolable. We know the question is not confused. What we don't yet know, what the next chapter is for, is what the answer is. Or whether the answer is one thing or two things or something that depends on which theory turns out to be right, which is its own kind of answer. The question sits here, unresolved, waiting. That is exactly where it should be. The question has been here the whole time. Every chapter, the horizon that announces nothing, the curvature of time, the dying star, the singularity without an address, the slowing light, the shadow we photographed, the tidal gradient, the warmth at the edge of nothing, the information that may or may not survive, the bridge in the equations, the ergosphere where stillness is forbidden, the energy extracted from geometry, the pairs spiraling toward merger, the physical reality of spacetime as a dynamical field. All of it was preparation. All of it was context. The question was always, can a black hole destroy the thing it lives inside? And now it is time to actually answer it. Not perform the answer. Not circle it beautifully and leave. Give the most honest account currently available of what the physics says, where the physics runs out, and what the uncertainty looks like when you hold it directly rather than at a careful distance. Start with what general relativity says plainly. General relativity predicts that inside every black hole formed by gravitational collapse, the matter that falls through the horizon continues compressing. The curvature of spacetime increases without bound as the compression continues. The geodesics, the paths through spacetime that particles and light follow, terminate in finite proper time. They reach a point where the geometry fails, where the metric, the mathematical object that defines all spatial and temporal relationships, can no longer be extended, where the curvature scalars, the numbers that measure the strength of the geometric distortion at a given point, diverge to infinity. The geometry breaks, not the matter inside the geometry itself. The space-time, the physical field we established in the last chapter as real, dynamical, capable of carrying energy and waves, reaches a state at the singularity where its defining properties become undefined. Infinite curvature is not extreme curvature. It is the failure of the concept of curvature. It is the field ceasing to be a field, the description ceasing to describe anything. In the language of general relativity, yes, a black hole destroys spacetime at the singularity, locally, specifically. At that point, or along that space-like surface inside the horizon that all future directed paths approach, the geometry does not just fail to be smooth, it fails to exist. Now here is what makes this more complicated than a clean yes. The singularity is hidden. This is Roger Penrose's cosmic censorship conjecture, first proposed in 1969, still unproven after more than 50 years, but widely believed to hold in generic physically realistic scenarios. The weak form. Singularities produced by gravitational collapse are always hidden behind event horizons. The outside universe, the spacetime you and I inhabit, the geometry that contains galaxies and light and time, is causally disconnected from the singularity. Whatever happens to the geometry that cannot propagate outward, cannot send signals, cannot influence the causal future of the exterior spacetime. The destruction, if it is destruction, is sealed inside. This is a partial answer of a specific kind. Not, the singularity doesn't destroy spacetime, but the destruction is contained. The event horizon is not just a one-way door for matter, it is a one-way door for the damage. The geometric failure at the center cannot reach out and unravel the geometry you are sitting inside. The exterior spacetime is protected, not by anything preventing the singularity from forming, but by the causal structure of the black hole that ensures the singularity's consequences are trapped. Cosmic censorship, if it holds, means the answer to "can a black hole destroy spacetime" is yes, but locally. Yes at the singularity, not here, not the spacetime of the observable universe. Just the bounded interior region, sealed from the rest. The damage is real, the quarantine holds. But cosmic censorship is not proven, and its status has become in recent years more complicated rather than less. The strong form of the conjecture that generic gravitational collapse produces spacetimes that are fully deterministic outside the horizon has encountered genuine mathematical difficulties. Charged rotating black holes, described by the Kerr-Newman metric, possess a Cauchy horizon in their interiors, a surface past which predictability fails even before the singularity is reached. Whether this Cauchy horizon is stable, or whether infalling radiation destroys it, restoring determinism is a question whose answer, in the fully non-linear setting, is still being worked out. Recent mathematical results suggest the Cauchy horizon is, in some regimes, unstable, that the singularity forms there and determinism is restored. But the proofs are not fully general. There is also the question of naked singularities. If cosmic censorship fails, if there exist physically realizable situations where a singularity forms without an event horizon, then the geometric failure is not contained. It is exposed to the causal future of the exterior spacetime. The damage reaches out. An observer in the exterior universe could, in principle, receive signals from a region where the geometry has broken down. A 2025 paper on dilatonic black holes argued that quantum effects, Hawking radiation combined with the Schwinger effect, inevitably lead to a naked singularity in the late evolution of certain types of black holes. The result is contested. But it is contested seriously by serious people, which is different from being dismissed. The window behind me is fogged at the edges. The room has gotten warmer than I realized. I notice it now move to the second framework. What does quantum gravity expect? The general consensus, and consensus is the right word here, not certainty, is that the singularity is not a real feature of physical space-time. It is a real feature of general relativity's prediction. It is what general relativity produces when you push it past the domain where it is valid. The theory breaks down at the Planck scale, at lengths of about 10 to the power of negative 35 meters, energies of about 10 to the power of 19 giga-electron-volts. And the singularity is what you get when you run the equations past that boundary without correction. The expected correction is quantum gravity. In loop quantum gravity, the singularity is replaced by a region of extremely high but finite curvature. The geometry does not break down. It bounces. The collapsing matter reaches a maximum density set by the Planck density, roughly 5 times 10 to the power of 96 kilograms per cubic meter, and then the quantum corrections to the Einstein equations generate an effective repulsion that stops the collapse and drives an expansion. The singularity is not hidden or quarantined, it is absent. The geometry continues through the bounce into a new region of space-time, possibly a white hole, possibly something we don't yet have a word for. In this framework, the answer to the title question is no. A black hole does not destroy space-time. It compresses the geometry to a Planck scale minimum, and the geometry continues, altered, extreme, but intact. This is the expectation. It has not been confirmed. Loop quantum gravity has not produced a fully worked out, observationally testable prediction about the black hole interior. The bounce is predicted by the effective equations of loop quantum cosmology applied to the black hole interior. It is a compelling, physically motivated, mathematically consistent prediction. It is not an observation. String theory approaches the singularity differently. The fuzzball proposal, which replaces the classical black hole geometry with a dense quantum structure made of strings and brains, removes the singularity by removing the interior. There is no space-time inside the horizon in the fuzzball picture, not in the conventional sense. The information that would have formed the singularity is instead encoded in the quantum state of the fuzzball surface, at or near the horizon. The geometry terminates not at a singularity, but at a boundary defined by the quantum structure. The singularity does not form because the geometry never extends that far. This is a different kind of no, not. The geometry continues past the singularity, but the geometry stops before it reaches the singularity gracefully at a quantum surface that encodes everything that fell in. These two no answers, the LQG bounce and the fuzzball truncation, are incompatible with each other. They cannot both be right. The physical picture they describe is entirely different. Both claim to resolve the singularity. Both lack direct confirmation. Now the third framework, the emergent spacetime possibility, which we touched in previous chapters. If spacetime is emergent, if the geometry is built from quantum entanglement, if the metric is not fundamental but arises from a more primitive quantum substrate, then the question of whether a black hole destroys spacetime is not quite the question it appeared to be. Spacetime in this picture is something like a phase of the more fundamental quantum system. The singularity, where the geometry fails, might correspond not to the destruction of something fundamental, but to a phase transition of the underlying quantum degrees of freedom. The geometry ceases to be a reliable description, but the thing the geometry is describing, the quantum substrate, continues. The fabric doesn't destroy, it changes phase. This is, I want to say it carefully, this is not a resolution. It is a reframing. It pushes the question one level down. What happens to the quantum substrate at the singularity is a question that no current theory answers. The emergent spacetime frameworks are, at this stage, more a research program than a theory. They point at a direction without having arrived there yet, but they suggest that spacetime is destroyed might eventually be understood the way the temperature of a gas is destroyed when you heat it past the point where the gas phase description applies. The underlying thing is still there. The description that worked before no longer does. So, the honest answer, in general relativity, yes. The singularity is a local destruction of space-time geometry, a point or surface where the physical field fails, where the geometry ceases to be a geometry. It is hidden from the exterior universe by the event horizon, protected by the cosmic censorship in generic cases, but real within the interior of every black hole formed by gravitational collapse. The field does not just become extreme at the singularity, it becomes undefined. In quantum gravity, in every serious attempt to extend general relativity to the regime where it breaks down, no. The singularity is an artifact of an incomplete description. The real geometry described by the correct theory continues through the region where general relativity predicts failure. The destruction is illusory. The geometry might bounce or terminate gracefully at a quantum surface, or undergo a phase transition, depending on which framework turns out to be correct. The current situation is that we have a theory, general relativity, that says yes with extraordinary precision and internal consistency, and we have the expectation, grounded in how physics has worked every other time a theory produced infinities, that a more complete theory will say no. We do not yet have the complete theory. We have fragments, proposals, calculations in idealized settings, predictions that cannot yet be tested against observation. What I think, and this is opinion held with genuine uncertainty, is that the singularity as general relativity describes it is not the final answer. The infinities are a symptom, not a revelation. Every time physics has encountered a true infinity before, the infinity has been a signal that the framework needs extending, not a window onto literal physical infinitude. The ultraviolet catastrophe, the divergences of early quantum field theory, the Big Bang singularity, which loop quantum cosmology replaces with a bounce. The pattern is consistent, but the pattern is not a proof. The damage is local. The quarantine likely holds. The geometry of the exterior universe, the space-time you inhabit, the field that carries light and bends around mass and expands at cosmological scales, is not threatened by the singularity sealed inside a black hole's horizon. Whatever is happening at the centre of Sagittarius, a star right now, 4 million solar masses of intractable geometry doing whatever it is doing in there, it cannot reach out and affect the sky above you. The destruction, if it is destruction, is contained. And it may not be destruction at all. It may be the edge of a description rather than the edge of a geometry. It may be the place where space-time as a concept hands off to something else, something the next theory will name and the theory after that will understand. The geometry of this universe is, as far as we can determine, intact. The question of what is happening in there, past the horizon in the deep interior, at the place where the map ends, remains open in the only honest sense, not as a mystery preserved for atmosphere, but as a genuine gap in human knowledge that real people are working to close, with real mathematics in the present tense. We don't know. That is not a comfortable place to rest, but it is where the physics actually lives right now, and there is something, I think there is something, worth sitting with in that. The universe contains places where our best description of reality fails. We know they exist. We cannot see inside them. We are building slowly the language to understand what they mean. The question has been asked honestly. The answer is still being written. There is a version of this question, what happens after, that most of us deflect without quite noticing we're doing it. We ask it about small things. After the project ends, after the season changes, after the people we love are gone. And we get reasonably good at holding those afters without being destroyed by them, mostly by not looking directly, mostly by staying close to the present and letting the future be theoretical. The universe's after is different only in scale, and scale, it turns out, changes things considerably. Right now, at this specific moment in cosmic history, 13.8 billion years after the Big Bang, the universe is in an unusually active phase. Stars are forming, planets are forming around them, galaxies are colliding and merging and producing new generations of stars from the compressed gas of those collisions. Life, in at least one location we know of, has organized itself to the point of lying awake at night thinking about black holes. The universe is, by the standards of what it will eventually become, extraordinarily busy. This will not always be true. The star formation rate is already declining. It peaked roughly 10 billion years ago and has been falling since. The gas supply that feeds new star formation is finite, and it is being consumed, and over the next few trillion years it will be exhausted. Stars will stop forming. The ones that exist will burn through their fuel and die, the most massive ones quickly, the small red dwarfs over timescales, onward stretching to 10, 20, perhaps 100 trillion years. Long after our sun has exhausted its hydrogen and expanded into a red giant and collapsed into a white dwarf, cooling over billions of years, the smallest stars will still be quietly fusing hydrogen, dim and stubborn, keeping at it, but eventually the last one will go out. This phase, the transition from a universe with stars to a universe without them, is called the degenerate era in the long-term projections of cosmology. What remains after the last star dies is a population of cold remnants, white dwarfs slowly cooling toward absolute zero across timescales of quadrillions of years, neutron stars, cold and dark, black holes, all sizes, scattered throughout what used to be galaxies but are now dispersing collections of dark objects drifting apart as the gravitational structures that held them together slowly dissolve. The universe at this stage is dark, not the darkness of night, which is full of light if you look far enough. A real darkness. Photons are still present, but cold, stretched to radio wavelengths by the expansion of the universe. Too low in energy to trigger any photochemical process. Too sparse to illuminate anything. An observer, if any observer existed, which is itself deeply uncertain, would see nothing with any conventional sense. The remnants drift, the white dwarfs cool, the geometry of space-time continues expanding, the dark energy that drives the acceleration of the expansion continuing its work, pushing the remnants farther and farther apart on scales that the old galaxy clusters can no longer bridge. On timescales of 10 to the 34th years or longer, the numbers here have stopped being numbers in any experiential sense. They are just sequences of zeros that the brain processes without receiving. Proton decay may occur if the proton is in fact unstable, as some extensions of the Standard Model predict. If it is, white dwarfs and neutron stars dissolve over these timescales, their constituent protons decaying into lighter particles, the last of the ordinary matter disintegrating into positrons and photons and neutrinos. The cold remnants come apart. If the proton is stable, and we don't know, no experiment has yet detected proton decay, the white dwarfs persist longer, but eventually quantum tunneling processes cause them to collapse into black holes anyway. Over timescales so large the number requires scientific notation with a 3-digit exponent. Either way, either path, the destination is black holes. The universe outside my window is doing its star-forming, galaxy-colliding, light-producing thing with complete indifference to what I'm about to describe. The black hole era. This is what cosmologists actually call it. A period so long it dwarfs everything before it. The stellar era, the degenerate era, the whole 13.8 billion years of cosmic history to date, the way the ocean dwarfs a cup of water drawn from it. Only black holes remain as significant structures. All other matter has either fallen into them or decayed or been dispersed beyond any relevant gravitational reach. The universe is black holes and the radiation field and a deepening cold. And then the black holes begin to evaporate. Slowly, stupendously slowly. A stellar mass black hole, as we calculated in Chapter 8, takes something on the order of 10 to the 74 years to evaporate completely through Hawking radiation. A supermassive black hole of 1 billion solar masses, the kind we've been discussing, takes roughly 10 to the 96 years. These numbers sit in the black hole era the way a Tuesday sits in geological time, but the process is real, and it runs in one direction and it does not stop. Each black hole in its time shrinks. The Hawking temperature rises as the mass decreases. The radiation rate increases. The final moments of evaporation, when the black hole has shrunk to near Planck mass, are a burst of high-energy radiation, a brief flash, and then nothing. The event horizon closes to nothing. The sealed geometry resolves. Whatever was inside, whatever the singularity was, whatever the quantum gravity theory that we don't yet have would describe, it ends. The last black hole evaporates. The last Hawking radiation disperses. The last active physics in the universe completes. What remains is thermal radiation, photons and neutrinos and perhaps other particles spread across an expanding space-time at a temperature so close to absolute zero it has no practical distinction from it. Dispersing further, cooling further, no structures, no gradients worth the name, no events that produce anything meaningfully different from what came before them. This is the heat death, the final state. Not a dramatic ending, no crunch, no collapse, no explosion, just the thorough completion of every process that had somewhere to go. The entropy has reached its maximum. The gradients that drove every event in the history of the universe, temperature differences, pressure differences, the uneven distribution of matter and energy that powered every star and every storm and every thought, have been smoothed out. The universe is not destroyed. It is finished. There is a difference, and I think the difference matters, though I find it genuinely difficult to say exactly why. There is a concept called Poincaré recurrence, the theorem that any finite physical system given sufficient time will return arbitrarily close to any previous state. The timescales involved are so vast they make the black hole evaporation timescales look brief. 10 to the 10 to the power of 100 and something years. Numbers that require exponent towers to write. But in a universe of finite volume with finite entropy, the theorem suggests that fluctuations will eventually, across these timescales, spontaneously reproduce structures. Reproduce atoms, reproduce in principle anything that has ever existed. Whether our universe is the kind of system to which this theorem applies is genuinely uncertain. The expansion of the universe may prevent it. The specific thermodynamics of dark energy may prevent it. It may be that the after is not a frozen stillness, but an unimaginably slow cycling through states that no observer will ever be present to witness. I don't know what to do with this. I've thought about it at different hours and it produces different responses. Sometimes it seems like a strange comfort. Nothing is truly final. The mathematics insists on return. Sometimes it seems like the most desolate image in physics, fluctuations in a cold, structureless universe, assembling and dissolving over incomprehensible timescales, with no continuity, no memory, no thread connecting the assembled state to anything that came before it. The return, if it happens, doesn't remember the original. I want to come back to now, to this specific hour, this specific darkness, this that has followed 15 others through the interior of black holes, and the structure of space-time, and the temperature of the quantum vacuum, and the long spiral of pairs, and the question of whether geometry can be destroyed. All of that physics is happening right now, not as history, not as thought experiment. Sagittarius. A star is sitting at the centre of the galaxy. 4 million solar masses, the geometry sealed, the Hawking radiation too cold to detect, the deep interior doing whatever it is doing. Somewhere in the universe, a massive star is completing its silicon burning phase. The iron core growing, the final week before collapse ticking down. Somewhere 2 supermassive black holes are 3 light-years apart and tightening. Somewhere the last light from a white dwarf cooling toward darkness is crossing the space between one unremarkable region of an unremarkable galaxy and another. The universe is running all of its processes simultaneously, at every scale, in every stage. The after is real and far, the now is real and here. There is something about having spent this many hours inside the extreme physics, the broken geometry, the lost information, the thermal radiation from nothing, the pairs spiraling in silence. That makes the present feel more specifically itself, not more fragile, more actual. The contingency of a universe complex enough to form black holes and also form the things that wander about them is not something the physics explains. It is something the physics sits inside. The geometry of space-time is intact tonight. The last star hasn't died. The last black hole hasn't evaporated. The gradients are still running. Something is still happening. And that, I think, is where this ends. Not with a resolution to the questions that don't have one, the singularity, the information, the quantum gravity that remains unfinished, but with the simple fact that the physics is real and the universe is continuing and the questions are genuine and being worked on by people who take them seriously. The geometry that might or might not be destroyed at the centre of every black hole is the same geometry that carries the light by which you read, and the signals by which you hear, and the structure within which every moment of your life has occurred. The question was never just about black holes. It was about what the universe is made of, whether the fabric is permanent or contingent, fundamental or emergent, destroyable or not. We don't fully know. The answer is being assembled, piece by piece, calculation by calculation, in the papers and the arguments and the late-night work of people who've decided this is worth their time. It is worth the time. It has been worth these hours. Sleep well. If this series has meant something to you, if these hours spent inside the deep physics have been worth something, the most direct way to help this work continue is through Patreon. This channel has no institutional backing, no sponsorships, no algorithm feeding it. It runs on the time I put into it and the support of people who find it worth supporting. If you're one of those people, the link is in the description. Even a small contribution changes what's possible here. Thank you genuinely for listening this far.